Good afternoon. If we could just have everyone please be seated. Thank you. If you'd like to find some seats, we welcome you to join us today for our Concrete Sustainability Forum, and this will also have a panel discussion at the end of the session. We ask at this time if you would be so kind as to set your cell phones or any of your electronic devices, if they would be set to silent or vibrate, as to not to interfere with the program and the discussion. We also would like to remind you that this is not allowed to be photographed, video, or audio otherwise unless approved by ACI, and that the information presented by the speakers does not necessarily represent the views of ACI. Just as a reminder, this is an AIA and CES approved session, and we will have codes that will be available. There we are. ACI is a registered provider of the American Institute of Architects Continuing Education System. There we go. Sorry, I was a little light on that. So you can earn your 4 AIA CES LUs, Health, Safety, and Welfare, and Sustainable Development Units, which is critically important to a lot of us. Also, this is a registered GBCI program, and you will be approved for 4 credits through GBCI. This is the Green Building Certification Institute. And in so much as that, you will see codes that will be coming up for each section of the Sustainability Forum. The learning objectives you can read as follows: understanding the impact of climate change and resource depletion on structures and high-performance buildings, identify opportunities to mitigate the impact of earthquake, tsunami, and climate-related disasters on communities and structures, understand opportunities to balance the need for safety, durability, and resilience with environmental stewardship and economics, and finally, identify opportunities in the concrete industry for structural concrete, life safety, material selection, concrete repair, and enhanced durability to impact resilience and sustainability. And now I would like to turn this over to Koji Sakai, Chair of ISO TC71 and SC8, for the introduction to our Concrete Sustainability Forum. And I was remiss in telling you who I was. I am Julie Buffenbarger, Chair of ACI Committee 130.
Good afternoon, ladies and gentlemen. So my name is Koji Sakai, and I'm moderator of this session. Before we get into the introduction, I'd like to invite the ACI President to give you a few words. Jim White.
Thank you, Koji and Julie. Welcome, everybody. I hope you're looking forward to a very exciting afternoon. On behalf of the Executive Committee of ACI, I would like to welcome all of you to this event and welcome you to Toronto. The Executive Committee are here with me, and I'll ask them just to stand up quickly. Vice President Ann Ellis, Vice President Bill Rushing, Past President Ken Hover, and Executive Vice President Ron Berg. So thank you all for being here. We're only going to be here for, thank you. I apologize that we can only be here for a few minutes. We are in the midst of our Executive Committee meeting, which takes place on Saturdays. And then we continue on Tuesday because we can't get everything done on a Saturday. But I do want to welcome to you, and this is the 5th anniversary meeting of the ACI Concrete Sustainability Forum, so beginning to become a rather permanent part of the fall meetings. And it's my understanding that today you're going to have discussions and presentations that focus on construction of safe, durable, resilient buildings and communities, maintaining a careful consideration of environmental stewardship. And after the formal presentations, I understand there's going to be a panel discussion, and the panel discussion will cover not only the topics that are presented today, but other topics that have been discussed in all of the previous sustainability forums. So again, on behalf of the Executive Committee, I wish all of you to have a very successful meeting, and we're looking forward to the progress that you make today and are able to report back out to ACI. So thank you all again very much for being here.
Okay, thank you, Jim. Now we will start the forum. Before we have the lecture from the 5 speakers, I would like to introduce the Concrete Sustainability Forum in the past and this time. So we had a 4 forum in the past from St. Louis, New Orleans, Pittsburgh, and Cincinnati. This year, this is the 5th anniversary forum. So I'm really excited. The last forum, we had, this shows the topics in the forum 4th. So the first part consists of the situation of the ISO standardization and also ACI 130 committee work and how to incorporate LCA into the code and standard. There are many standard codes, and also we had ISI rating tools which were developed by infrastructure sustainability, I think that's the initiative. And also we had 2 technical presentation. One is a low carbon concrete, and the other one is low carbon buildings. And lastly, we had the essence of the sustainability, lessons from Japan disaster, which was presented by me. So this was the last forum's presentations. And what are the conclusions from the forum 4th? So number 1 is the Japan disaster represented the real meaning of sustainability. And then we need to get back to the origin of concrete and concrete structures from the sustainability point of view. Therefore, we need to develop the innovative technologies in concrete, and also this is very important, we need to incorporate sustainability aspect into design system or construction system. So this was the conclusion from forum 5th. So this time we set the theme of the forum 5th, which say that balancing safety, durability, and resilience with environmental stewardship. There are many things that we have to consider in our activity when we design structure, when we construct structures. So this is a big topic. So I really hope that we can have the good presentation and also good discussion for that. And today's, we have the 2 parts. The part 1 is the presentations by 5 speakers. First presentation is the HEI 318. Mr. Orlando Poston is the chair of the HEI 318. He's going to talk about sustainability in the HEI 318 structure concrete building code. And then we have the Professor Doug Fulton from the University of Toronto. He's going to present the improving concrete sustainability by designing and specifying 4 durability aspect. And also we have the speaker from the University of Toronto, Professor Michael Collins, is going to present the improving the resilience of critical infrastructure. And then we have the Canadian Standard Institute, Mr. Michael Mortimer. He's going to present the title, The Adapting Built Civil Infrastructure in Canada to the Impact of Climate Change, a cause and standard perspective. And finally, I'm going to present essentially what does concrete sustainability mean. The last forum I also presented these topics, but I modified and add something to that. So I hope that you can enjoy all 5 presentations today. And part 2 is the panel discussion facilitated past President Florian Barth. And finally, we invite all speakers and discuss speakers and the participant from the forum. And finally, we have the wrap-up by Julie Buffenberger. And after that, this program, we will have the reception immediately after this forum. So the room of the reception is Essex Ballroom. Please note this is a new location. So this is the what we are going to do this afternoon. Enjoy the forum. Now, I'd like to invite the first speaker, but before that, let me know that each speaker has 25 minutes, including 5 minutes question time. So we will show you remaining time 5 minutes if time comes. So please finish within 20 minutes. So the first speaker was Mr. Randy Foster.
Thank you, Professor Sakai. Looking at the speakers this afternoon, it was clear that I was chosen as the token American on the program, and also probably the token person representing the ACI 318 building code, although I'm chair. Certainly my knowledge base has been somewhat limited, but I've, with the current building code cycle that we're in, I've certainly learned quite a bit in terms of looking at sustainability in the building code, and I appreciate the opportunity to come this afternoon to talk to you. I think the thing that we have to keep in mind about building codes, the perspective is that we're specifying minimum requirements for safety. I think that's the key. That doesn't mean you can't provide other types of resilience, durability, serviceability, but certainly the focus in building codes is to make sure we have life safety in our structures and in our buildings, and that has to be our primary focus. But we have to have these other foci, if you will, in order to make a robust building code. I recently had the opportunity to be in Paris, and of course everybody that is involved with building codes always says the first building code was the Code of Hammurabi in the Louvre Museum, and found it very fascinating looking at that, thinking about this this obelisk type structure from almost 2,000 years before Christ. The interesting thing is I went to the back side of the Code of the Stone of Hammurabi and I noted a point in the code and I took it back to a cryptologist at the University of Texas at Austin, and it had a thing there that says, "Thou shalt make sustainable structures," which I found very interesting. So we're not the first to think about it, and certainly not going to be the last to think about what we need to do in the design and construction of concrete structures to make them durable, sustainable, and it is a challenge for in the design process. Of course, the kind of the real jumping point, if you will, was the Brundtland Report in 1987 that started again, it wasn't the first time it was ever talked about, but certainly talked about on the world stage about sustainable development. And I think some of the key things that led us into 318 this year to kind of look at this code cycle, what we can do to ensure that we have sustainable structures. Development that meets the needs of the present without compromising the ability of future generations to meet their own needs. certainly I think that's a very, very important aspect of our life here on this earth and leaving it to the next generation. I think kind of a subtext of that regarding the environment is where we live, and development is what we all do in attempting to improve our lot within that abode. And to that end, those two have to be inseparable. So again, some overall arching themes about, I think, as engineers and other professionals in the concrete construction industry that we need to think about in terms of design. In the Brundtland report, I guess the title was Miss Harlem Brundtland, who was a former Prime Minister of Norway, had been selected to lead this commission or working group from a United Nations designation, and I think it was very important work and really a very good timing in terms of the world and what was happening in the world with the resources. I think the other further thing that really came out of the Brundtland report were what are the pillars of the sustainable development, and certainly economic growth, environmental protection, and social equality kind of represent the pillars of the stool, if you will, three-legged stool, which we need to stand on in terms of our design. It's hard for me to separate my role, as I have two jobs, and one job is to be a structural engineer, and the other job is to be chair of the 318 building code, this code cycle. So I'm going to talk a little bit about my look at sustainability as a structural engineer, and one of the projects that I'm most proud that I worked on was a very simple structure, but it really represented, I think, the key to what we're talking about in sustainability. It's the repair of the Marina Del Rey seawall, which is in Los Angeles, California. Wrote an article with my colleagues on the project that appeared some 13 years ago in Concrete International in 1999. And Marina Del Rey was the largest man-made small craft marina in the United States. It was built by the Corps of Engineers in the late 50s and early 60s, and basically just north of the LAX airport. And over time, it's actually owned by Los Angeles County, and they essentially lease land for development over a long period of time. After, in the mid-1980s, 1986, they started to have failures of concrete panels, simple cantilever walls, and became pretty clear soon that in 7.5 miles of wall that made up the various basins and channels that something was going to have to be done. So we had, 60s to 85, some, 26, 27 years of life out of this existing concrete structure. There were a total of 728 panels, and the overall development cost in that area was something on the order of about $5 billion over the year. So it's a very substantial investment by various private individuals on essentially what's public land. And so we had to assess the condition of the seawall and design for the repair. It was obviously clear once we got into corrosion problems, but of course the other thing in the late 50s and early 60s, there really was not any consideration for the seismic upgrading. And the other challenge we faced is you see the basin in the middle of that red there just north of LAX. It's in the middle of what they call liquid earth. And so these are all areas in the Los Angeles area that represent high probability of liquefaction during earthquake. And one thing, the challenge we found as a structural engineer is when you have that type of material short of digging caissons or rehabilitating the soil behind it, there's very little you can do, and the cost of that is extreme. And we look at the economic challenge of sustainable structures, and I tell everybody one piece of paper that I have in my file that I always will have in my file locked away in a firebox, and that is a letter from the building safety person at Los Angeles County that says we're not responsible if there's liquefaction in this area. So I have that hidden away just in case it ever comes back to try to haunt us. But it provided the uniqueness of it, provided the challenge of here's the structure we have to repair. There's all these things that we have to deal with, but there's not enough money in the world to deal with them. So you can only deal with certain realities, and the reality of that was to make it stable for typical for the corrosion aspects that obviously had deteriorated the structure, and also to upgrade it seismically for a more moderate earthquake, not one that would produce a high level of liquefaction. Cantilever wall, joint reinforcement, and if you look at that construction joint down there, you can see obviously that's the point of vulnerability. There was no water stops. You got a tidal action several times a day over 25, 27 years, water leaking through. You can imagine what the condition of the reinforcement was at that joint. And the interesting thing was the joint in that near region was certainly had a lot of loss of reinforcing steel, statically determinate structure, but the rest of the reinforcement for the most part on the back side of this wall was in pretty good shape. And we were able, the project kind of evolved about looking at replacement to other types of armament, if you will, in terms of protection, and we were able to identify the damage on the back side of the wall using some non-destructive techniques, namely impact echo, and these are the types of things that we're able to identify on the back side where you had delaminations of reinforcement and what areas they were occurring in. So the system ended up being, as a retrofit, repair and rehabilitation for strengthening, were caissons that were tied back to the wall. We had to utilize, of course, the existing reinforcement both horizontally and vertically, and this action and the number of caissons was dictated by the amount of damage we found. All wall panels had to have at least 3 caissons in order to strengthen the wall, but in some caissons, because of their condition, had to have 6. But by prioritizing those panels and also doing a custom look, if you will, at each panel, we were able to save on average 2.6 caissons per panel, which was a substantial amount of money. So again, the overall concept were these caissons. There was an impressed current cathodic protection system that was put in place to protect the existing reinforcement that we were counting on. And I do this again because as a structural engineer, and the kinds of things that we have to look at in a building code, whether it's the 318 code or the new repair code that's coming out by ACI, the economic challenges that we have. In this particular case, this work was done for, and the reason I said it's not a very, in terms of the engineering necessarily, the most challenging, but we were able to save a substantial amount of money by increasing the life of the structure from something that had been 25 years that we believe is certainly going to get another 40 years, and replacement costs were in the range of $200 million plus. The FIB model code talks about their new 2010 code about performance requirements for sustainability. And they note they have several things under Article 3.4 in their code regarding performance, and that all aspects of design, construction, use, conservation, demolition, as well as recycling and disposal that are relevant to the environment and society are taken into account. That's a pretty bold statement, pretty broad statement in the context of design. Not sure what it means, but I guess part of their effort in the code and what you'll see we're doing in 318 will be the challenge of what we mean by sustainability design. Of course, the initiatives and focus really gained some steam under ACI, former ACI President Florian Barth and former ACI President Dick Staley, God rest his soul. And we were challenged, all technical committees within ACI were challenged to develop its documents aimed at including sustainability principles. Well, the current code, 2008-2011 code, if you go into 1.1.1, again, it pretty much clearly conveys what the purpose of the building code is: provide minimum requirements for design and construction of structural concrete members in the context of a legally adopted general building code. So, it's really, again, about safety, minimum acceptable standard for materials design and construction practice is really the focus of the building code. And also, may or may not know, as part of the effort of this code cycle, the going through a major reorganization. It's kind of the first reorganization probably in about 45 years for 318. It's going to be what we define as a member-based code. There's going to be essentially one chapter for each type of member, and the reason we're doing this is we found in industry that because a lot of the design was spread over multiple chapters, that people were missing code provisions and were not complying with the code. When you go through a code chapter designed here on a beam, you're going to know at the end of that chapter that you've completed all the requirements for a beam. And it's kind of broken out into administrative chapters and what we call toolbox chapters, but the focus is that green there that are member chapters, and then the decision was made that earthquake-resistant component of design is still going to be kept separate. There have been a lot of changes over the last several cycles with that. We didn't want to disrupt the design community, even more so than we were already doing. Then we have chapters on reinforcement materials and detailing, and then the overall at the end is the construction process, of course, and that's where the QA, QC requirements are going to be located. Don't need to look at a lot of this. These just kind of highlight those major divisions and administrative global requirements toolbox, and this is really where the meat of the design in 318 is going to be done. You've got one-way slabs, two-way slabs, all the way down. We're also going to have a new chapter for diaphragms and collectors, and this then completes the other part of the code requirements or sections in the new reorganized code for 314. Again, ending with the construction, as you would do in the design process, the construction process. Those are going to be all collected at the end of the code. So here was our first attempt on 318. One thing you're going to find out is we don't make decisions very quickly on building code. It takes a long time. It takes a lot of votes, and a lot of times they don't go through. So chapter 4 is a new chapter called Performance Requirements for Structural Members and Structural Systems. It's new. We felt like there needed to be kind of an overarching chapter that kind of represented what the design guidelines were for in the member chapters, and so that is, of course, a logical position where we might include something like sustainability. And so the first attempt was materials and components of structural concrete shall comply with the sustainability requirements in the general building code. Well, there were lots of negatives. Here's one negative. I agree that sustainability is becoming more important, but to state that all thoughts of any committee 130, for example, shall be followed is way too strong. Let's see what they develop and what we might reference. Until then, delete this sentence. So that was the first ballot. Here's the fourth attempt. Sustainability, section 410. Materials and components of structural concrete shall comply with minimum sustainability requirements in the general building code. Well, appropriately, one of the negatives was, well, what are these minimum sustainability requirements of the general building code? They went to the IBC, the International Building Code, which is basically the model code that most of the United States follows. I looked in the IBC and found nothing. Let's add this when there's something to comply with. Pretty fair statement, I believe. So here's the final approved text that the committee agreed on. So we have section numbering had changed a little bit. 4.9, the licensed design professional shall be permitted to specify sustainability requirements in addition to the strength, serviceability, and durability requirements of this code. Well, it's a pretty weak sentence in a lot of ways, but at least has the concept of sustainability, and you can see that the focus there is we don't want to do anything in sustainability that's going to harm the minimum safety requirements of the building code. That's really what the kind of the subtext of the message is there. 4.92 just then goes on and says that strength, serviceability, and durability requirements shall take precedence over sustainability. So it kind of reinforces that idea. In order to provide some emphasis in Chapter 4, we felt like we also needed something in Chapter 1, which is the introduction to the code, after all. And we're on the 5th ballot here, and we still don't have it approved. So just to give you an idea of how tough this job is, really all we're doing is adding something on the right-hand side there, which is the commentary. The purpose of this code is to provide for public health and safety through structural strength and stability. this code is intended to be compatible with sustainable design principles that do not conflict with public health and safety. Pretty innocuous statement in our mind, apparently not to a lot of committee members. So we're on the 5th ballot of that. I think we may end up being successful with some additional wordsmithing, but those will be essentially the 2 locations that the 318 building code will identify aspects of sustainable design. Well, what does that really mean for the designer? We're doing this, and there's a lot of words, and what do they really mean? And I think, for a structural engineer or specifier, we're talking about what we can do, and Professor Hooton will certainly discuss about the material aspects and durability. We want to optimize concrete mixes so that we make them more workable, durable, improve strength and aesthetics. They have longer service lives, they have less maintenance, lower cost, and all those things kind of feed into this concept of sustainable. And it's things that, as I think, as structural engineers, maybe we haven't given ourselves enough credit over the years that, in fact, that's what we have been doing. We just didn't call it sustainability. So we're recognizing now that some of the things that we do in design, in fact, can lead to sustainable development, lead to longer life, and for the general good of society. So what's the summary here? As you can see, it's something in the code. We got a long ways to go. We're certainly not going to get much further in this code cycle where we're at. Certainly, I think what we've done is add to the code and take the charge from former President Barth and Staley very seriously, and have something in the code at least in the spirit of sustainability. So with that, I'd like to conclude my presentations and be glad to take any questions. Thank you very much.
Thank you, Mr. Poston, and the time is just 20 minutes.
Thank you.
And we have the 5-minute question time. So if you have the question or comment, raise your hand, state your affiliation. Is there any question or comment on the floor?
That's because we don't have much in sustainability in the code. So, hi. Yes.
So, very interesting presentation, but we also understand the challenges you have when you're working with a life safety code. Recently, I was in Washington, D.C., and they're talking more about the development of sustainability, or I should say its growth and its maturity into more of a resilience message.
Mm-hmm.
So while we could not really specifically address sustainability per se in 318 as it stands, as its present definition, how do you foresee in the future that perhaps, I know I'm putting you on the spot, I apologize for that, but how you can address the resiliency topic that seems to be coming out so frequently? We see the U.S. government has widely adopted this, like in their codes, are mandated by an executive order to look at resiliency and sustainability. So from that perspective, how do you foresee in the future that perhaps 318 could address this newfound maturation of sustainability?
Well, I think obviously we need to build on what we have, and we recognize that there's and resiliency is something very important topic in a broad sense of what we want to achieve out of any structure, and it's certainly an important concept and something that we really don't actually key on directly in the code, and we would need to do. I think what we had started thinking about originally, which is where I think we probably need to go in the building code, is to have a formal chapter in the code on sustainability and resilience to broaden the message in terms of design. Of course, the challenge is, and I think what we have to do is give up the idea that we're only specifying minimum requirements for life safety. It's a change in definition of what the building code is really meant to be, and you know that's I think been hard for engineers to kind of accept. But I think if we broaden that definition, then we will broaden the scope of what the document can be and provide more performance-based requirements that lead to sustainability and resilience in design and construction.
Okay, we do have an internet question so that's why I'm sitting over here as I'm fielding some of the internet questions. This is a webinar that is being all over the world, and actually we're very nice to have a question from Brian of Qatar. He asked, this ACI 318.14 is the latest code. When will it be available?
Yeah, I get asked that question all the time. So I'm way down on the pay grade, so I have to respond to my uppers. But actually, we should be finishing the code by late next year, 2013. There is, of course, a public comment period that goes through consensus. Its publication is slated for summer of 2014.
Okay, thank you very much.
Is there any other questions or comments from the floor?
Well, hearing none, thank you very much. I appreciate the attention.
Now we have the next speaker.
Okay, good afternoon, everyone. Pleased to be here. I had to come down the road on the subway to get here from the university. So I'm going to talk about a couple of things. We'll talk about designing and specifying for durability, and that has to do with performance specifications and how they could help improve sustainability. But first of all, I'll jump around a bit, and I'll acknowledge John Bickley, who is at ACI here, and he'll be speaking a couple of times, but he's not here this afternoon. And he and I have worked on a number of performance specifications on large structures, where we've tried to incorporate some of the concepts. And I do a lot of work on materials things, so I don't look at all the sustainability issues, obviously. And we know that Portland cement contributes a significant amount to global CO2 emissions and to global energy use, and that there's a lot of, and it's the clinker component, the clinker manufacturing in Portland cement that consumes that, or generates the CO2 and consumes the energy. So, but Portland cement isn't a product, it's not a final product that we use concrete. However, 90% of the carbon footprint of concrete approximately is from the Portland cement. Now, if you replace some of the Portland cement clinker, if you get the clinker content down, you can reduce the total cementitious content, you can do a whole bunch to reduce the CO2 impact of concrete. We've got to look at the bigger picture as well, and this is the NRMCA put out a fact sheet a few years ago, which is probably too small to read, but anyway, there's a lot of things that go beyond just the concrete materials, and I want to just mention that at least, that the concrete's made locally, so the transportation is typically local transportation, it's not long-distance transportation. The thermal mass and the fact that they're fairly airtight make their thermal efficiency much better for a lifetime of use. They typically have long service lives, and their light color can have positive effects with the urban heat island effect, and they can incorporate recycled or industrial byproduct materials, and also they carbonate over time and will absorb some of the CO2 that they generated in their manufacture. Now, just to explore a couple of those issues, concrete, the CO2 or the energy, embodied energy in a building, is only about 10% of that's from the initial construction, in the range of 10%. It might be 10 to 15. The rest of it's in the lifetime use of the structure. So all the power and HVAC requirements are what eats energy. So if you can make an impact in your design using concrete to reduce that, then you can have a much bigger impact than worrying about bits and pieces of the concrete mixture over the lifetime of the structure. And one of the ones, and I just throw this picture up of this building, which is just around the corner, a few blocks away, where they deliberately used exposed concrete finishes. It was high-performance concrete. They were getting close to 100 megapascal concrete in it, but they deliberately used good architectural finishes, light-colored finishes on the concrete to reduce the lighting they would require inside the building. That was a deliberate one of the design concepts, to use that. And then they don't have to put any finishes either on the floors or the walls because they won't have the VOCs from various interior finishes by leaving that exposed concrete. So there's another way. And the other way, of course, is to use the thermal mass of concrete in concrete elements to mitigate the HVAC requirements. And I'll show that just north of the city, about half an hour north, is called the Earth Rangers Center that was built. It's a multi-level structure, but they incorporated a whole bunch of things in that structure, including earth tubes and that's just a picture of the earth tubes coming through. All the intakes of the building go underground through an earth tube that's about 30 meters long, a series of these earth tubes that precondition the air. So in hot weather, the air underground is cooler, and it cools the air before it gets into the building for the HVAC uses. And in the winter, it warms the air, the cold air, before it comes in. So they're not taking minus 20 air. It gets into about 5 or 10 degrees before it actually enters the building just by going through these earth tubes. And they have to be made of concrete because corrugated steel tubes allow water to form and other types of tubes that allow bacteria and fungi to grow, and the concrete prevents that. So concrete for these earth tubes is an important part of that design. They also use thermal mass in their design, and they've got embedded radiant cooling and heating in the ground tubes for their HVAC. And this building uses 90% less energy than an equivalent building of its size. So it's quite an impressive structure, and they're monitoring all this and updating their technologies all the time. And it was a LEED Gold, and they're now going for LEED Platinum on the operation of the building. Okay, so I have a chair that's called an industrial research chair funded by the Cement Association and the federal government on concrete durability and sustainability. So these are some of the topics I'm looking at. I'm doing a lot of durability research on various types of aggressive environments because we want to extend the life of concrete so that it is more sustainable over the long term. We're looking at developing new durability-based performance specs because we're trying to put new test methods and use them in specifications so you can quantify performance in various aggressive environments and then use performance criteria rather than prescriptive criteria to evaluate the mixtures that are put forward. And we're trying to develop and promote performance-based specs, and I'll spend some more time talking about that. And particularly on the 10%, the reducing the CO2 footprint of the concrete that's used in the first place. We've got a lot of students working on Portland limestone cements, which were introduced, and I'll talk about that. Looking at the synergy of these Portland limestone cements with traditional supplementary materials like fly ash, slag, silicone in multiple blend binders, which are becoming more common. We're looking at combined aggregate gradations, which is not new, but it's new to the Canadian code. To look at trying to optimize the combined aggregate gradation, because if you can do that, you can reduce the required cement content and actually improve the properties of concrete, reduce the permeability, reduce shrinkage, and other things that are good. And we're looking at non-Portland cement binders, non-alkali activated materials, and we're doing work with recycled concrete aggregates. Now I'll mention a couple of these things. So we can do all these things at once. A lot of these things, they're not individual. There are individual things you can do, but you can usually do almost all of these things simultaneously, and we are doing them. If you can reduce the cement content, as I mentioned, from combined aggregate gradations. Of course, water-reducing admixtures will allow you to use less water, therefore reducing the paste content of concrete, which allows you to get more aggregate in. The Portland limestone cements reduces the clinker content of cement. And the way we've designed these Portland limestone cements, they have equivalent performance to Portland cements, so you're not losing anything. It's fairly transparent to the users. And of course, we can use cement replacement materials such as fly ash and slag. And where recycled aggregates, I think, is one where we have to use them where appropriate, and but we can use them. So the problem with the aggregates, and I think a number of agencies in the U.S., various state highway agencies, and others have recognized this in the past, we're just a little slow on the uptake, that meeting the individual coarse and fine aggregate gradations leaves a gap in the middle. You end up with a gap-graded mix. And it's a huge impact in urban areas because they're blasting these quarries, they're sieving it out for coarse aggregate and throwing a whole bunch of undersized material away that's not allowed in the specification because of the gradation envelopes. And then they add up with the sand and they end up with a gap where the stuff they've just thrown out would fit. We're doing work on that for the industry. And just to show that, if you take an intermediate size aggregate, that would could fill in the spaces. And this is typically done more so in Europe where they have multiple bin silos. This hasn't been the North American tradition to do that. And if you look at a grading curve, if you just took sand and stone, you end up with that little gap in the middle. And it doesn't look like much, but it causes you to have issues. And filling that gap in the mixes with 35 MPa or 50 MPa concretes, we were able to reduce the cement content of the mix for equivalent performance by about up to 16% of the cement binder composition of the concrete. So it's not a trivial loss of cement, but you get the same performance with less cement, and then you're not throwing away some of these quarried materials that were expensively crushed or blasted and crushed, and especially in urban areas where we're having to haul aggregates as much as 100 kilometers now to bring them into the city of Toronto, because they're not allowing any new quarries on the Niagara Escarpment, which is our traditional aggregate source. That's about 50 kilometers away, and they're having to go further afield for aggregates in the city that is growing rapidly. So it's a dilemma. In 2008, we introduced a new class of Portland limestone cements. I was actively involved with doing that. It's up to 15% underground limestone, and that was eventually adopted in the concrete standard and eventually in the building codes in Canada. And effectively what that does is gives you the same performance with 10% less CO2 production. So it's a big deal for the cement industry because they potentially face threats of, CO2 caps or taxes on their CO2 emissions based on point source emissions. So they've got to reduce their point source emissions. British Columbia already has such a legislation in place, and it's costing the industry. So the limestone cements helps them get there on top of what they were already doing. Now, such cements have already been used in the U.S. for almost 10 years now under the 1157 performance spec, specifically in Utah and Colorado have been two states, DOTs, that have allowed that. And finally, in 2012, the Blended Other Cement Code 595, which is spec'd by more people, has adopted some 1L designations with up to 15%. So it's going to become a bigger issue. And we've been involved not only with the lab work that led up to this, but we've been involved with field trials with the MTO, the Highway Department here in Ontario. We did several of them. This is just some barrier walls where we did some trials a few years ago to try and get things going, and we use them together with the traditional slag that's used as the local supplementary material in the Ontario market. And just to look at performance, these concretes with Portland limestone cement or the cement, looking at strengths 1 day through 91 days, they've got equal performance right through from 1 day to 91 days. The shrinkage is no different. Freeze-thaw durability is no different. The de-icer scaling, the test we did was no different. And the Coulomb values are essentially, in terms of permeability, are well, they show slightly better here, but I would say they're not different because of other tests that we've done as well. So without changing anything, they've got 10% less CO2 and through more clinker reduction. And we've done this in other studies. We're doing a lot of work on sulfate resistance. And just to highlight the top row, if you just took a plain Portland cement concrete, these are 0.4 water cement ratio concretes. These are strengths 7 days through half a year, with about 90% clinker content in that cement. But if you go down to the other one I've highlighted down there, with 15% limestone in the cement and 40% or 50% slag, we're only using 38% clinker in that concrete. So we've reduced the CO2 burden on the concrete by about half. And again, we've got equivalent strengths, maybe slightly less, 500 psi less at 7 days, but higher strengths at later ages, and so with big reductions in the CO2. And if you go to the permeability, huge differences versus Portland cement if you use the limestone and the slag. Again, we're seeing much lower permeabilities. It's not having any negative impact on the potential permeability of the concrete. So again, with reducing the CO2 burden, we're able to do that. We've done some trials on sidewalks, just actually about this time last year, up on one of the highway interchanges is being updated, and we're using increased percentages of recycled concrete aggregate replacing the coarse aggregate. We only used 25 up 15% and 25% replacement to see if it could be used in concrete exposed to freezing and salt exposure. It's only been out there a year, hasn't been exposed to salt because the intersection isn't open yet, but has been exposed to freezing. That's just dirt sitting on top because I didn't have a broom with me. You should always go prepared to the field. But what you see here is the field. There's absolutely no scaling, there's no pop-outs anywhere on that surface, and you'd expect if it was going to get exposed to freezing with porous recycled aggregate in there potentially, you could have pop-outs. We didn't see pop-outs after a year. The air contents were about right. The strengths were close on these at 28 days. There was an increase in the permeability values with the increased RCA, but they're still less than the 1,500 we would require. The durability factor, what's interesting is that this C666 freeze-thaw test, you can see the performance dropping off way quickly. Not the de-icer scaling performance, but the freeze-thaw, because you take small beams, 3-inch cross-section beams, you put these porous aggregates in there, the concrete is fully saturated from when you cast it till you start the freezing cycle at 14 days, and it never dries out. So in that case, those porous aggregates act like porous aggregates that are fully saturated, and they break apart. So it's an artifact of the test procedure. In the field, we're not seeing that because, of course, the recycled aggregate acts like porous, lightweight aggregate that will release its water as internal curing for the concrete, and it won't be saturated unless you're pouring on November 1st or some days. But we did, and it didn't happen. So the concrete does dry out sufficiently that we're not getting that effect in real life. But if you do the standard test, if you only did laboratory tests, you'd say, well, this is no good. We wouldn't use it. So we need to look at adopting the test methods to accommodate the realities of the material, because the standard test methods we use, like 666, aren't reality-based test methods. They don't relate well to field performance in a lot of ways. And just for your information, if you landed at the airport, all the new aprons and around the terminal have ½ a meter of recycled concrete aggregate as granular base underneath, because they recycled all the concrete from the airport when they replaced 2 terminals now and all the series of runways and aprons. They recycled the whole thing, about 140,000 tons. And of that, about 75,000 tons got used as the granular base. And apparently they found that, recycled aggregate makes a great granular base, and it's actually cemented up and improved the structure of that pavement. It also saved a lot of trucks coming down the highway from over 50 kilometers away from the closest quarry to bring aggregate in for that purpose. So it had a number of uses, and they're slowly using the rest of it. You can actually see the residual piles if you look certain ways at the airport, on the edge of the airport property. So we can do a whole bunch of good things to reduce CO2. In the mix design, we can optimize aggregate gradations. We can extend that with microfine fillers. We can use the underground limestone. We can use SCMs. And we can make concrete that has reduced permeability, reduced shrinkage. We can reduce the cement clinker content of the concrete and up to strength. And potentially, and we've done this in the lab, if you look at a bar chart, I know it's difficult to see here, but the cement's the gray bar on the left, and the Portland cement component on a volumetric basis. With the traditional Portland cement concrete, we might use 12% by volume Portland, and by incorporating combined aggregate gradations and fillers and underground limestone and SCMs, we can get that down to about 3%, which means you could get down to about 160 pounds per cubic foot of, I guess that's cubic yard, that's my mistake. I translated it back. I don't know imperial units anymore. It's pounds per cubic yard of cement. We could get that down to about 160 pounds of cement per cubic yard and not mess with the concrete too much. We can make these concretes. So that's a big improvement. How's my time doing? Am I good? 3 minutes, great. I'm going to get nowhere with this. Okay. What I wanted to talk about was this thing about performance specifications, because durable concrete is sustainable concrete. The longer we can extend the life of concrete, the longer that CO2 gets, that embodied CO2 and energy gets spread over the life of the structure. And that has a huge impact on reducing them. And premature deterioration is not what we want. So anything we can do to improve the durability of concrete will extend that lifetime, so we're not out there doing rehabs prematurely on things that could have been prevented with proper design. And durability means more than just listing concrete materials in mixed proportions. There's a whole bunch of things that are difficult to put in a code that need to be controlled, temperature control, protection of fresh concrete, curing, proper inspection, who does the inspection and testing, and we need performance and objective-based standards to make these things successful. Randy mentioned the FIB code. Some of the other components in that code is that they require you to actually design for durability. You actually have to do a service life calculation for whatever the durability exposures are, and they actually have equations that they set up as forces and resistances in a durability-based design in that code. The also thing is they require the builder or the owner to be provided with a birth certificate of the building. Basically, what was the design assumption, the design calculations, what were the requirements, and what were the actual results achieved in the construction process. And as well, they've got to provide the owner with a maintenance manual. Just like when you buy a car, you get a maintenance manual in the glove box, and you open it up and it says how often you have to change the oil or do various maintenance operations. And for the various parts of the structure, the owner is required or provided with this information. So you've got to replace your joints every 15 years, this sort of thing. And look at the bearings, and they've got to factor that into the design. That if there's going to be maintenance required, they've got to actually incorporate to make it feasible to do that maintenance as part of the design process in the building of the first structure, so that it's not impossible to do that maintenance. So that's something that's pretty interesting, and I know it's a long way from what the ACI code is doing now, and I think it'll be a long time before we go in that direction. But I think it's an interesting approach. It'll be interesting to see how this is just being rolled out now in Europe to see how that's going to perform. We have a performance spec in Canada. We've had it since 2004, and we revised it in 2009. We're now revising it again for the 2013 concrete standard. And one of the things that, and it's basically meant that all concrete, with a few exceptions, is turned into performance specifications in Canada. It's an option, but because of the way we've worded it, nobody wants to take on the prescriptive option anymore. Because of we identified the roles and responsibilities to the owner, the contractor, and the supplier. And the owner or the owner's representative don't want to take on the responsibilities of performance specs. Because when we identified the responsibility, if you're going to prescribe a concrete, then you take responsibility for the performance. And they're going, whoa, wait a minute. We just want to prescribe it and get the performance. So that, when that's clarified and the roles and responsibilities have been clarified, it's made people jump back, and we've basically moved to performance. And I won't get into this because of the timing. There's a lot of stuff going on in the U.S., and John Bickley and I and Ken Hover had a hand in doing things through the NRMCA that led to the ITG document on performance-based specs, and now the Committee 329 has started its work on developing an alternative performance specification for concrete at ACI. And if you'll forego the, well, I guess we either have discussion or I give you an example. It's up to Mr. Chairman. John Bickley and I worked on a large specification, a draft specification for some large expansion of mass transit. Basically, they had mass concrete. Some of these sections were 3 meters thick, 10 feet thick. They were all below the water table, so prevention of cracking was a performance requirement. We know that the structures aren't going to be in service for years, if not multiple months, so 28 days isn't a criteria except from a scheduling point of view. And they wanted air-entrained, low permeability concrete, 35 foot MPa. So we had to figure out what are the objectives. We needed to state the objectives, not state what you got to do, but what are the objectives. They want leak-proof concrete because they don't want water coming in because they've had experience with leakage and corrosion, and they don't want water getting in. And they also, because even though these things are underground, they consider them the same exposure as a parking deck or a bridge deck, because they say people track the insult on their feet in the wintertime, and occasionally with the cold air of the transit, they get freezing on the surfaces. So it is possible that you're going to get leakage through the mass concrete, but it's far more likely you're going to get leakage through the cracks and joints. The primary objectives are to minimize cracking. So we need to, in terms of a specification, set temperature limits and differentials, set shrinkage limits, allow permeability and strength limits to be extended out to later ages, 90 days, if possible, and use permeability-related performance specs rather than water-cement ratio if it helps reduce the cement contents. We minimize the thermal gradient, and we want to design it to minimize crack widths. And one of the things we wrote into this performance spec, so we actually wrote this performance spec, and a number of the jobs have used this concept. We require the contractor, the contractor to work with the supplier to develop mixes, and we require them to use a monolith test, which in our case suggested a cubic meter of concrete with insulated forms. They have to, instead of casting cylinders and doing the trial mixes with 6 by 12 or 4 by 8 cylinders, they cast a cubic meter of concrete with thermocouples in it, and they look at maximum temperatures, differential temperatures in the insulated mass, and then they take cores. Their tests are all done in cores taken from that structure. So not on things stored in a 28-day moist room. And some of these elements have actually used bigger sections, some of them 2-meter sections, based on the thing. So they've adapted this concept of using a monolith pour in their specs. And this is one we did one trial mix with a supplier, and just shows if you have the temperature variations during the day at the surface and just near the surface. And there's the internal temperatures, take it up to 60, and their gradients were about 20 degrees in this particular concrete mixture that they're evaluating. We said, look, if you want 35 MPa, make it at 90 days, but if we're going to test on cores, you've got to take 85% of that for acceptance based on cores, so it's only 30. We said, look, we take in-place air content and air void distributions rather than fresh air contents, at least in terms of the specification for pre-qualification, and we allow them to use the rapid chloride test, even though for service life, because they want 100 years from these structures, that they use chloride diffusion test. We're saying you've got to calibrate that, because from a construction acceptance point of view, a diffusion test takes about 3 or 4 months to finish, and it's a useless test for an acceptance criteria. It's great for pre-qualification, useless for acceptance. So get a rapid test in there just as a surrogate for that during the construction acceptance process test. We wrote that in, and so we said it. And the same with shrinkage. We set a shrinkage spec. There is an option in the Canadian standard. And we set gradients. We set 55 as our maximum, with the maximum gradient of 20. And we tell them they can't take the forms off and covers off until they get within requirements of the CSA table, which has maximum temperature criteria for that. We have some commentary about that given to them with the spec, saying, well, these are sort of the objectives. And what are you going to have to suggestions on how they get there. One of the things is that the quality control is the responsibility of the contractor. They use certified labs, and they have to report that to the owner. Any problems that arise, they've got to communicate those and figure out how to correct that so it doesn't proceed too far. One of the issues that brings up in the Canadian standard, we reference that in the spec, is that there's joint responsibilities of the contractor and the supplier. The owner is contracted with the contractor, not the supplier. The contractor contracts with the supplier, but they've got to work together if you have an end result specification that the owner is buying from the contractor. So they've got to learn to work as a team, and that's worked quite well in a number of things. I won't go through that. I've got 2 slides. So we actually did one of these pores station. They had 3 pumps going. They're pumping it to 2.2 meters thick using large aggregate. They did a number of things. They controlled their temperature. They were getting the low permeability, and actually monitored this large pore. It was 1,200 cubic meters. They got to 54, so they just made it on the 55, and the gradient was generally less than 20, with one exception in one corner. We could have used higher slag contents in that mix. They only used 50%. They could have used lower total binders to meet the requirements, but the owner we couldn't convince the owner because he interpreted the whole mass concrete as a chloride frost exposure, as opposed to the outer layer that was going to be added later. And so we had some issues with that. Again, one of the key to make this work is pre-tender, pre-pour meetings, so people understand the objectives of what you're trying to do, what's special about this concrete if you're going to do something that's sustainable or durable. Because if you don't have everybody in the loop on the objectives, it may not happen in reality. So just putting on paper isn't good enough. You've got to have meetings so everybody's in the loop. We've done this on a number of jobs with a lot of success. So anyway, there's a lot of changes that can be made on the mix designs to reduce CO2 in the concrete in the first place. But if we can extend the life of structure, we can extend that cycle and make the life cycle CO2 burden and energy burden much lower. And performance specs can, through understanding what's required and specifying that, increase the chances of maintaining durability and providing the flexibility to use more sustainable mixes. So that's my message. That's where I took so long. Yeah, sure. No problem.
So my name is Michael Collins. I'd like to share with you some thoughts on how we can improve the resilience of concrete structures. Over on the left, we see the Hanshin Expressway in Kobe and what it looked like in January of 1995. That's not a resilient design. It wasn't an unexpectedly large earthquake. It was a design from the 1960s. On the right, we see a nuclear power station, Pickering, just in the eastern portions of Toronto. It's also a design from the 1960s. Here we see a few examples of unexpected occurrences. A gas explosion in a resort in Mexico, a terrorist explosion at Moscow airport, floods in Queensland, Australia, and floods in a town that we're in now, Toronto. That was Hurricane Hazel that killed 81 people and caused $1 billion of damage in this city. How can we ensure that when we build a city like this, and more importantly, when we look at it now, how can we ensure it's resilient and that if something unexpected happens, we don't suffer in a disproportionate way? And I'd like to go to my hometown of Christchurch, New Zealand, to draw some lessons that might be valuable for other cities around the world. Christchurch is on the Pacific, and it's built on the estuary of a river. It's the Avon River, which is here coming to the sea at a delightful little place called Sumner, where we have a summer house. Most of you, if you even think about New Zealand, think of it as a little tiny place down there in the bottom of a big ocean, a long, long way from where you live. So if I pick it up and take it up and put it off the coast of California, you get a better sense of how big it is and where it is relative to the equator and the regions near the pole. And you see it's about the size of California, and it stretches from about Vancouver down to Santa Barbara. And it's very geologically similar because it's in the Ring of Fire, and the topography of California and New Zealand are rather similar. The Pacific Plate is moving in against the Australian plate at the rate of about 2 inches a year. And in the complex way they come together, in the North Island, the Pacific Plate goes under the Australian plate, and at the bottom of the South Island, the Australian plate goes under the Pacific Plate. So in the middle there's sort of a twist as they go from bottom to top. There was one previous earthquake which destroyed a city in New Zealand. That was the city of Napier in 1931. This is about the end of the major fault, the Alpine Fault, which passes right up the spine of the South Island, and that's Milford Sound. These mountains that you see there, they're about 5,000 feet above sea level. Most of the places, the plateau of peaks is about 10,000 feet above sea level. My geologist friends tell me that if there hadn't been glaciers, the mountains would now be 20 kilometers high. They aren't. They're about 3 kilometers because they've been ground down. And that shingle is all on the plains. It makes the plains. The people of Christchurch recognize they're in a seismic risk zone, but they were worried about the Alpine Fault moving. There was a major earthquake, sort of nearly magnitude 9, about once every 300 years. And it's about 300 years since the last one. So sometime soon there'll be a major fault on the Alpine, major earthquake on the Alpine Fault. So in 1990 they started a program to get ready for this and prepare the lifelines in the city so they could have a chance of sustaining this event. Here's the National Seismic Hazard Map for New Zealand, or for this part of New Zealand, released in 2010. And what you see is the 500-year peak ground acceleration is high where that Alpine Fault crosses across towards the North Island. That's the sort of crossover place. And there the peak ground accelerations get up to 0.85 G, whereas Christchurch is in a low seismic risk region, and the peak ground acceleration was said to be 0.22 G. So that's what was designed for. September the 4th, 2010, after the publication of that map, there was a magnitude 7.1 earthquake, which caused peak ground accelerations of about 0.3 G in Christchurch. So not too far off. But near the earthquake, they were about 1 G. And the earthquake was also in what was supposed to be a low seismic risk zone. The earthquake occurred on a fault that hasn't moved for at least 15,000 years. And the faults were not known because they were buried under about a kilometer of gravel from the mountains. Amazingly, nobody was killed. There was a lot of damage. The earthquake happened at 5 a.m. on a Saturday morning. And there was a lot of unreinforced masonry that lost their facades. And there were a couple of taxi drivers injured in taxis that were pummeled by the falling masonry. Notice the railway tracks in the middle there and how they reacted to the ground shaking. 8 days later, there was a service of Thanksgiving in Cathedral Square, the center of the city. They didn't have it in the cathedral because they still weren't sure about the safety of the cathedral, so it was outside. And all of those multi-story buildings around performed magnificently. And the general sense was we've done very well. Everything's good. And the structural engineers in the city and in the country set about evaluating all of the buildings. And they red zoned some, red stick at some, green stick at others, and orange stick at others. Of course, those of you who haven't been through an earthquake might think an earthquake is one event, but it's not. Since September the 4th, there have been 3,905 earthquakes in Christchurch of bigger than magnitude 3. And there you see the biggest magnitude for every 2 weeks since then up to October the 18th of this year. And you see a few of the big ones. 7.1 was the first one. By the way, there were 834 quakes that week. And then September the 22nd, we were there in Christchurch on that day. The magnitude 6.3 hit, and that week there were 514 earthquakes. And that day there was more than 100. Here you see some of those 3,900 earthquakes that have hit since the original one, which is the green star that you see that was about 25 miles out of the city. You see the red line just under that green star, that's the ground fault, the Greendale fault, which actually was shown on the surface of the ground. And then you see the way the dots, the red dots, move towards the city. And that February the 22nd is a star which is buried under those dots. And more recently, they've been moving out to sea with the pink dots. And the house we have is buried right under all those blue dots. We're right on the edge of the sea. Here's a satellite map showing where the epicenter was, and you can see where the center of Christchurch is, the central Christchurch business district. And there's a photo taken just as the earthquake hit. There's the city being destroyed as all sorts of masonry buildings collapse and lots of concrete buildings collapse as well. Why did this happen? Well, here's the peak ground accelerations measured at a number of stations around the city. What you see is we had vertical accelerations much more than 1 G at a whole series of places. And we had horizontal accelerations much more than 1 G as well, approaching 2 G in some places. Remember, the design level was 0.22 G. Here's the trace from one of the seismographs closest to the epicenter, and you see the vertical accelerations going up to 2.2 G, and the horizontals bigger than 1.6 G. Notice that the earthquake's very short. The strong motions only last about 5 seconds, and that saved a number of buildings. I'm mainly going to talk about the tall reinforced concrete buildings in the central business district, but I can't resist going to the hill shaking and rockfall near where our house is. Our house is on top of that cliff. There's our house. There's what happened to the diagonal braces. 4-inch by 4-inch treated pine snapped. 6 of them snapped. And if the earthquake had have been much longer than 5 seconds, the house would have gone over, I suspect. There's my office. Liquefaction. Randy mentioned liquefaction. We learned what liquefaction meant that day. We drove through that, trying to get to my wife's mother, who lives alone and was 99 years old at that time. And we visualized her buried under furniture. A 20-minute trip took us about 2.5 hours. There's what the roads looked like. And there's what the cathedral looked like. And the fallen masonry. And there's the local newspaper, the press. And one of the things you learn when a huge emergency, unexpected event happens in your city is newspapers are very important. The power was gone. Nobody saw television for weeks. The press's building was destroyed. People were killed on the top floor. But you know what? 6 a.m. the next morning, they delivered the paper. Every subscriber got a copy of the paper. And it came every day, and it was the center of information. Also, huge numbers of people, the majority of people who were saved by passers-by. By the time the professional rescue squads got there, most of the people were dead. So there were construction workers downtown fixing the damage from the first earthquake, and they helped greatly in pulling people out, but it was by and large just volunteer passers-by. Here's a typical modern, high-strength, reinforced concrete building, luxury office building, a lot of lawyers, a lot of expensive rental space, and it survived the earthquake fine. The only trouble was the stairwells collapsed, and so the people inside couldn't get out. And it took 6 or 7 hours to get the cranes in and get them out. And these enterprising bunch of lawyers are coming down, belaying down. There's the sort of stairway collapse that happened in a number of the reinforced concrete structures. This is in the tallest building in the city, Grand Chancellor Hotel. There's the hotel with some of the damage. There's if you want to get your car out of the parking garage of that hotel. And this is the sort of rubble that's all over the place in the cities. Walking around the city a week or so after the earthquake, we saw building after building like this one, which just survived. I mean, you can see how it's on the verge of failure. My specialty is shear failures, and I have tested about 800 relatively large beams in the structures laboratory that's just up the street from you here in my 43 years at the University of Toronto. In the few days in Christchurch, I saw more shear failures than I've seen in the rest of my life. Here's a apparently modern, nice-looking building. Actually, it was designed in 1963. Pine Gould Corporation building. And it was one of the 2 reinforced concrete buildings which totally collapsed in the earthquake. It killed 18 people. And this is one where the professional firefighters managed to rescue a number of people. And here's 2 particularly joyous survivors who've come out after a fair number of hours buried under the rubble. And here's the worst disaster. 182 people died that day, and 115 of them died in this building. This is the so-called CTV building, Canterbury Television, and it had a number of tenants in the building. One floor of the building was occupied by a medical clinic whose previous building had been red stickered, and they had to move out in September. And this building was green stickered, so they moved in, and all of them were killed. And the building they moved out of them is still standing. And imagine what the structural engineers feel like who green sticker this building. Why is it so bad? Can you see those little columns? Those columns are really small. Not only are they really small, they have incredibly tiny amount of transverse reinforcement. Look at it. Little wires. That's because these were designed as gravity load only. They're not part of the seismic force resisting system. And so you don't have to have this building was designed in 1986, incidentally, long after good seismic provisions were in place. What's going wrong? Well, we've done a lot of study developing models that can predict behavior. And as soon as I managed to get the details on this building in March of 2011, I ran an analysis, a simple analysis, which an engineer could literally run in 5 minutes once you got the details. And what it showed is that column under the high axial load that's on it, this was my estimate of the axial load, turns out it was quite good, shows that that column cannot take more than ½ an inch of movement. So if you have a differential movement between the bottom and the top of ½ an inch, bang, the column is gone. That's what we call drift. And it's translating to a drift of about 0.3%. It's totally unacceptable. And 115 people died because of that. Here's another building I looked at. And to my eye, this one was on the verge of failure. And so we did a slightly more elaborate analysis. This takes a couple of days. And based on that, we predicted that the building is where that black spot with the purpley drawing is, and total failure is just a bit further on. And so again, we predicted, I think, quite well, and you can see in the drawings under the final failure where the failure would be, and those green squares are indicating near failure in the joints, which is where you would see the problems. Now, we may say that the reinforced concrete buildings and the steel buildings in Christchurch performed admirably, with the exception of those two I showed you that collapsed catastrophically. The people in them got out. Relatively few, hardly any people died in the modern buildings. They got out. But then, immediately after the earthquake, engineers said probably we'll have to demolish about 20% of the buildings. And then as they looked at them more, and as more and more aftershocks hit, and in some cases buildings that had withstood the first fell down in an aftershock, including one that fell down with some inspectors in it, who luckily survived. As they looked at more and more, they realized that more and more have to be demolished. It simply wasn't feasible to repair them. And now over 800 buildings in the central core have been demolished. And the whole central core of the city has been dead for nearly 2 years. It's still cordoned off. And this city of nearly 400,000 people is just suffering greatly. It's been a catastrophe. Those are the buildings still standing, and the red ones are ones that still have to be demolished. The green ones are the ones that have been deemed to be repairable, and the blue ones they're still investigating whether they can be repaired economically. Here's a couple of positive stories. There's a steel building on the left, which was reoccupied in July, the first multi-story building to be reoccupied. And on the left, a combined steel concrete building, which is going to be repaired and performed very well in the earthquake, but it's in the cordoned off area, so it has not yet been reopened. Here's some even better stories. There were only 2 buildings in the city that had modern damage limitation structures. One was a women's hospital that had been completed in 2005, and it had base isolation with rubber lead bearings, a system that was developed in New Zealand in the 1970s and has been applied a number of places, but very few were in Christchurch. There's a lot in Wellington, which is regarded as a very high seismic risk. Christchurch was not a high seismic risk. This structure performed magnificently in all of the earthquakes that have hit, remained fully operational. The second one is a building using the press technology, the technology developed at San Diego some years ago, late 1990s. Precast, pre-stressed concrete panels held together with clever energy-absorbing dampers. And that building also performed remarkably well, staying fully operational during all the earthquakes. This is a slide from San Diego when they were doing the development of that press system. And the man standing up on the fourth floor is Stefano Pampanin, who's now at the University of Canterbury and was the designer of that hospital building, or at least a consultant on the seismic design. And this is really what the message of Christchurch is. Yes, as Randy said, our traditional objective has been life safety. And all of the engineers who designed their buildings were thinking about how can they make the building so no matter how big the earthquake, the people will get out. But you know what? That's not good enough. Because those buildings that stayed operational only cost, well, the base isolated hospital cost about 1% more due to base isolation. The press building hardly cost anything more at all. They couldn't identify any significant additional costs. So is it good enough to simply save the lives if the result is the whole community is destroyed? Because it's really questionable whether Christchurch will ever come back to what it was. So on the bottom of this diagram, it's what has been suggested in Christchurch, that it's unacceptable, no matter what the magnitude of the earthquake, that the building is non-repairable. The building should be repairable at any level of earthquake, because it's possible now. That technology exists. And here's back to the city that we're in now. There's a huge number of high-rise buildings here, you may have noticed, and there's an awful lot under construction. We have about 150 under construction right now. And near the CN Tower here are 4 more that are being proposed, 85-story high. There are difficulties in the design of concrete high-rise buildings. There are difficulties in steel buildings as well. One of them is wind vibration. 85-story condo, that really limits how high you can go, particularly for slender buildings, which many of them are. Seismic performance. It's not good enough that they stand up through the earthquake if they then have to be knocked down after the earthquake. And those high-rise buildings in Christchurch, only about 25 stories high, they posed a major hazard. They're the reason we had to cordon off the whole central city, because you have to look at where they're going to fall. The other problem is we only have about 1% critical damping. Yes, I will finish. I'm finishing right now. We can fix this. Here's one way of fixing it: viscoelastic coupling dampers, which have been developed at the University of Toronto. Rubber is a marvelous material, 200% shear strain. It tolerates easily. Full-scale experimental validation of this has shown wonderful performance. We can add up to 5% damping for expected events, and then under extreme events we can still get even more. And that really limits the damage. This compares a structure with these dampers to a regular structure, And the takeaway from it is there is much less damage with the frequently expected earthquakes, and the structure is easily repaired after the catastrophic earthquake that may occur only once every few thousand years. So I leave you with this thought. The maintenance of the works is the most important part of the duties of an engineer. Wherefore it's necessary that the engineer needs to know which of the structures is in need of having money spent upon them. And this is the statement of Julius Frontinus, who was the keeper of the aqueducts of Rome in the year AD 97. I believe our challenge is the same. Thank you. We don't have time.
Our next presenter is having a few technical difficulties, so that gives me a few minutes to introduce him. His presentation will be entitled Adapting Built Civil Infrastructure in Canada to the Impacts of Climate Change, a Codes and Standards Perspective. And we welcome Michael Mortimer, Project Manager of Canadian Standards of the Canadian Standards Association.
Thank you very much, Julie, and good afternoon, everybody. When Randy Poston presented, he says that he was the token American. I'm the token guru on this panel, and for those of you that don't know what a guru is, we're not talking about a spiritual Eastern leader. We're talking about the acronym GURU, general understanding but relatively useless. I'm very, very pleased. I was a little bit humbled, actually, by some of the earlier presenters. Many of these, two of the presenters, Doug Hooton and Michael Collins, are actually members of CSA technical committees, and I won't spend a lot of time on who CSA is. When you get the slide package, there's some information on who CSA is. But much like American Concrete Institute, CSA standards are written and approved by the members. Those people are the subject experts, not staff like me. Now, being a guru, there is one advantage to that, and that is that I can give you some outside perspective on climate change in a context that is somewhat broader than just concrete, although concrete for sure has a line of sight to this issue. All right, so what we're going to go over the next 15 minutes or so is we'll talk a little, I have a couple slides on the relationship between ACI and CSA. We'll talk about what I call Climate Change Adaptation 101. And for those of you here in the room, I'll have a quick fun pop quiz. For those of you that are on the webinar, you're just going to have to play along. You also heard about the Code of Hammurabi, and I just want to make one other comment. And Dr. Poston put up a slide on Hammurabi. I thought he was going to tell you about the very first building code because it was actually in that code. And interestingly enough, you heard Doug Hooton talk about performance specs. And not only did Hammurabi have the first building code, it was actually also the first performance spec. All right, and there's two criteria. You can correct me if I'm wrong, Doug, for performance specs. One is you have to have a threshold that you have to meet, either whether it's pass or fail or some sort of a threshold. Second is you need to be able to test for it. Okay, so the building code was very simple back then. If a builder built a house and the house collapsed and killed the occupant, the builder was put to death. That was the code. Now, if you think about it, it met the criteria for performance spec. It had a threshold, right? If the house collapses, right, it fails. And if somebody dies, that's no good. Okay, that was the test. If somebody got killed, that triggered. And then, of course, today we have different inspection and enforcement methods than they did back then. So it was actually a lot of firsts, not just the building code, but actually the very first performance code. I want to talk a little bit about ACI and CSA standards. They're complements, not substitutes. For those of you here in the room, if you work and live in Canada, can you put up your hand, please? Okay, for those of you on the webinar, about 2/3 of the room, I think, put up their hand. If you're working outside of Canada, put up your hand. Okay, so all of my examples today are primarily focused on the Canadian situation, but some of them are actually transferable. If you look at CSA in the area of concrete, whether it's materials, structural design, and specialized concrete products, we've got about 32 publications and 250 volunteer experts on about 20 technical committees. If we compare and contrast that to ACI, and Ron or Doug, you know, if I get the stats wrong, just let me know. I think you've got about 4,000 members on technical committees. I know you've got tens of thousands of members around the world on technical committees, 4,000, and way more than 32 standards and, 5 standards? 400 standards and publications. So as organizations, we're roughly the same size, but in terms of depth of coverage in the concrete area, certainly ACI is very, very important. So what's the role of CSA technical committees in this area? Because certainly we don't want to duplicate what's already out there. So there's 2 key roles. One is to address unique regional conditions, whether they're geotechnical, climatic, or Canadian load factors, and I'll talk a little bit more about the Canadian Building Code in just a couple slides, as well as environmental law. Also, clearly, all right, if you look at a lot of the CSA standards, and you heard a little bit this morning about one of the standards in the 823 series, they reference a lot of other international standards, including ACI. Here's some, this slide here is just some examples of some of the specialized topics that CSA covers in the concrete area, including the Canadian Highway Design Bridge Code, which is a model code for Canada. It's referenced by the provinces and territories. This is the key slide, though. And what this shows you here is the relationship between standards that are referenced in CSA standards on up. So in Canada, it's the 13 provinces and territories that have provincial building codes. So that's at the very, very top, the chevron at the very, very top. Each of those jurisdictions has membership. The regulatory authorities have membership on the Canadian Commission on Building and Fire Codes. That's which is the publisher of the National Building Code of Canada. That is a model code that's written in mandatory language, but until it's actually adopted by the jurisdiction having authority, it's voluntary. Once they adopt it, it's mandatory. So there's extensive references to standards, including a lot of CSA standards. You heard, for example, in the concrete area when it comes to materials and structures, both CSA 23.3 for structural design, as well as many of the 23.3 material specs are referenced. So key takeaway here is that as soon as we reference ACI standards as an example, ACI standards become part of the Canadian building codes, okay? So we're a gate, not only do we vet for local relevance, but we're also a gateway for international standards into the Canadian codes and standards system. Okay, now I'm going to change topics. I'm going to talk about climate change adaptation 101. And I'm sorry for you, for those on the webinar, you can't participate, but for those of you in the audience, please play along. This is probably the first time I've tried a pop quiz in front of a group this large, but we're going to go. So climate change adaptation, but before I start, if you haven't heard about climate change before, put up your hand. Okay, so nobody in the room put up their hand. All right, now, climate change adaptation. If you know what climate change adaptation is, put up your hand. All right, I got a few hands up and a lot of people are tentative. So here's the pop quiz. For those of you who said you know what climate change adaptation is, I expect you to get perfect on this question. I'm going to skip over this, this particular slide. Okay, so here's your pop quiz. Which quote most closely explains what adapting to climate change is? You actually have 4 choices. There's 3 on the slide. Okay, the first answer is shy at parties talk about global warming. It's a real icebreaker. Okay, just wait for it. You have 3 more choices. Climate lasts all the time, but weather only a few days. Okay, that's your second choice. Third choice, the weather forecast for tonight, dark. And that's George Carlin. There is actually a fourth choice, that's none of the above. So I'm going to take a poll right now. All right, put up, and for those of you in the room, if you think A is the right answer that best closely explains climate change, put up your adaptation, put up your hand. No hands up. B, climate change, climate lasts all the time, but weather only a few days. Any takers? A couple. All right. C, weather for, remember you got a fourth choice, none of the above. C, weather forecast for tonight, dark. I can't believe it. I've actually got some people putting their hand up. And D, none of the above. Okay, so the majority were for D, none of the above, and you're absolutely right. Okay, none of those really, although they're true for the most part, none of them really explain the adaptation side of climate change. I borrowed this slide from Toronto Environment. Okay, and even this slide has some limitations. What it tries to do is say, well, look, okay, mitigation, which is all about GHG reduction, it's global. If you're reducing your greenhouse gases and carbon, it doesn't matter where you are in the world. How you remediate emissions is always the same, but adaptation is very local, and there's some overlap. Okay, so that's their explanation. This, I think, is a better explanation, and I'm going to use two examples. The key, if you forget everything else I say, climate change adaptation or response always has to be local, okay, because the conditions are different. Now, Michael Collins talked about environmental hazards. He talked about one side of the coin, that's seismic events, all right? There's another side of the coin, that's atmospheric hazards. So when we're talking about climate change adaptation, we're talking about atmospheric phenomena, whether it's wind, precipitation, freeze-thaw cycles, and so forth, okay? On the left here, this was an event that happened in Toronto. It was August 2005. It was called Freaky Friday by the Property and Casualty Insurance. It's the Finch Avenue washout, just east or west of Sentinel and York University. And actually, these photos, you can actually see the sequence of how the washout happened. Now, this particular culvert was designed to meet, at the time, the 1 in 100-year event threshold. And that was actually Hurricane Hazel. And you heard Michael Collins refer to Hurricane Hazel that happened in 1950. So a lot of the infrastructure in this city, in the city of Toronto, was designed to withstand the Hurricane Hazel threshold, which we exceeded. Now, even though Finch was washed out, okay, there's a lot of and there was a lot of economic consequence, and quite frankly, Finch Avenue here was shut down for the better part of the year, okay? But we have other ways to get around. It was easy to adapt. There's a lot of adaptive capacity in Toronto. Now, compare and contrast that to the picture on the right. This picture was taken in the early 2000s. That's what's called a Super G petrol or gas tanker. They weigh about 60,000 kilograms. It went through one of the ice bridges on the Mackenzie Valley ice roads and bridges in the north. Okay, and the problem up there is that when you've got this type of an event, you don't have a lot of options to get resources, materials, and people to remote communities. So the impact is much more, the consequences of the failure are much more extreme, okay? So climate hazards for infrastructure, there's all sorts. There's more frequent extreme weather events. Extreme weather events in themselves are not necessarily a climate change phenomenon. Water damage, wind damage, very important for transportation engineers and builders is more frequent freeze-thaw cycles. And north of 60 in the northern circumpolar, the Arctic in Canada, melting permafrost. So climate-sensitive infrastructure, or infrastructure sensitive to atmospheric hazards, it's transportation, roads and bridges, homes and buildings. electrical transmission, energy transmission, oil and gas pipelines, even things like alternative wind energy structures, floods, coastal, lots of infrastructure that's vulnerable to increasingly uncertain climate and atmospheric hazards. So again, if you forget everything else about adaptation, this is the end of Climate Change Adaptation 101 or close to it. It's not primarily about GHG reduction or global warming. Yes, there's a little bit of an overlap. This is really about becoming more adaptable and resilient to either gradual or rapid changes in atmospheric phenomenon over a period of years and decades rather than days or weeks. So weather is about days or weeks, climate is about years and decades. Okay? So it's way more ubiquitous. So when we talk about developing adaptive responses to climate change, and what you're going to see is that there's very few standards that have climate change in the title, yet there's many standards that can influence responses to and adapting to climate change. Okay. In terms of solution development, a few years ago, and we've been looking at climate change adaptation for about 7 years now. Up until a couple of years ago, there was only one type of response to climate change at increasingly uncertain. That's no regrets actions, which is a way of saying over-design your infrastructure, which of course is not very feasible, particularly when we have minimum building codes and we have quantity surveyors and so forth. Since then, I'm pleased to report that there actually are some methodologies that are coming into their own. I'll give you an example of the risk-based approach. I'll tell you a little bit about the state of climate scenario projections and where throughout an infrastructure's long life cycle you can actually embrace opportunities. So there's a lot of ways that standards themselves can influence the adaptability of infrastructure. We're required to update standards every 5 years. That's part of our accreditation, so technology can be introduced. Updating using up-to-date climate data is very important. The S6 CSA Bridge Code, unfortunately, has historical weather data. Some of it goes back to 1968, and it's quite frankly not a good predictor of what climatic conditions are going to be over the useful life of a very long life cycle infrastructure. This is the principle of risk-based approach, and I want to give you an example of that. Essentially, there's two parameters that you look at. One is the sensitivity. What's the vulnerability to an event? If you think back to my slide comparing Finch Avenue and Sentinel to the Mackenzie Valley Ice Road, right? So sensitivity is one, but also the consequences. So the more extreme the consequences and the higher the sensitivity, the more important it becomes to develop a response. So that's at simplest, those are the principles behind the risk-based approach. In terms of predicting climate for the decades ahead, there's about 24 different international modeling centers around the world. None of those models are particularly accurate. So what most countries are doing is actually utilizing what they call as ensemble analysis. They won't just use one climate model. They'll actually use projections based on a combination of the models to try and increase the repeatability and accuracy. We talked a little bit about how life cycle and long life cycle in infrastructure provides windows of opportunity to actually upgrade infrastructure. And Michael Collins mentioned that not only designing up front, but maintenance is important. Of all the standards that we have that have some sort of influence on resilience, guess how many of them deal with operations and maintenance? Anybody want to hazard a guess? Versus design and build or repair and rehab. Anybody want to guess? 0. I mean, they're predominantly design build. When I mentioned, clearly you in the room, whether you're a structural designer or an infrastructure or an owner or operator, this is something you need to be concerned about. Property and casualty insurers are also very, very concerned about this. And like some of the other comments mentioned earlier, they'd like to see the building codes change to reflect climate change risks. We'll skip over this one. So in terms of CSA, we've done 7 special reports. Of the 400 standards that have some sort of a line of sight to built civil infrastructure, there's really 29 standards that have a profound impact on adapting to the impacts of climate change. Probably no surprise, a lot of them are in the structural design area. Okay, some of them are in the material science area as well. Just want to talk a little bit about, I think I'm probably down to 2 minutes or I'm out of time.
It's almost time.
It's almost time, okay. The ice storm in 1998 was a boundary event. It was way more than a 1 in 100 year event. The interesting thing, one of the outcomes from that, along with a lot of other forensic engineering studies, was that CSA's standard for C22 for overhead transmission lines actually introduced for the first time a risk-based approach and a probabilistic approach to complement deterministic prescriptive design requirements around transmission. So that was one of the outcomes. In terms of recent work, we're doing a lot of work in the Canadian North. That's the canary in the gold mine in terms of climate change adaptation. Warming in the circumpolar regions is happening much quicker. One example is the CSA plus 4011. It's the only guide or standard that actually uses climate change in its name out of all those 29. The key here is that in the north, ideally we'd like to build everything on bedrock. Then we wouldn't have to worry about melting permafrost or global warming. A lot of communities, that's just not possible. So permafrost becomes a key element of the foundation. So changing permafrost conditions during the useful life really means that you've got high risk of a failed foundation. So the guideline is an overview. It actually incorporates the risk-based approach. It involves more than just structural engineers. It's actually aimed at a multidisciplinary team, so they're not just looking about first cost all the time. I'll just wrap up. This is just taking you through some of the examples of some of the considerations that it goes from risk screening. It talks about how it incorporates the global climate ensemble analyses. Just in terms of concluding remarks, I just want to say, and this is taken off the internet, my favorite research source. The climate change scientist asked a bartender what 98% of the patrons were drinking that night. There was also a climate change denier in the bar, and that they asked the bartender what the other 2% were drinking. It doesn't matter, though. Here's the point. It really isn't about philosophy or ideology or politics. It's really about survival. And it's only recently that even climate change deniers are willing to look at climate change adaptation, because it doesn't matter whether you think it was man-made climate change or not. We're living in a time of increasingly uncertain atmospheric events. So it really is about survival. Both of them just recently are starting to accept that we really do have to adapt, and built civil infrastructure, whether it's concrete-based, wood, steel, really plays a role. And standards are playing a role as well. Thank you very much for listening.
Do we have any questions for the speaker at this time? I have one question for you. I don't rush off that easy. Certainly said that standards are playing a significant role in how we adapt to climate change, and I think that's very true. That 5 years ago when we started looking at sustainability, no one really looked at climate change. They looked at mitigation to climate change, but not adaptation.
Absolutely.
What role of, in your opinion, do we need to see changes in the way that we go about looking at standards to be more successful to adapting to climate change? And if so, if you could choose one specific idea that should be incorporated, what would that be?
Speak the language of engineers and structural designers. The problem, I mean, here's the plus and minus of adaptation. GHG, it's a mono issue, right? It's all about emissions reduction. Adaptation is way more amorphous and ubiquitous. It's just one of many stressors, right? Like wind velocity, more uncertain wind pressure or velocity, changing precipitation patterns, that type of thing. All of them have a line of sight back to increasingly uncertain atmospheric hazards, why ever they're occurring, but adaptation itself doesn't mean anything. So we have to speak the language of engineers and structures, which is looking at all the forces that an increasingly uncertain future state might have on our existing standards, and learning how to move away from risk, looking only at historical data, and figuring out some reliable risk-based approaches and probabilistic approaches that somehow can factor in reliably future states over the useful life of that infrastructure. So that was more than just one comment.
No, that's all right. Thank you very much. Are there any other comments? Yes, in the back. Could you step to the microphone, please, and ask your question?
So, civil engineer with Bechtel. I'm a little not concerned, but I was wondering if there are any sort of glossaries or standard definitions being used with climate change adaptation, because the USGBC and the University of Michigan just published a very long climate adaptation paper that I'm sure you've probably taken a look at, and they define the no-regret strategies as a strategy that will generate social and or economic benefits whether or not climate change occurs. So they're calling these no-regret strategies something that is a good-to-do best practice anyway, but in addition, it will contribute to making the structure or the infrastructure resilient. So are you guys kind of working on putting together some common terms so that everybody's speaking the same language?
Thanks for the question, Kelsey. It's a very good question, and the answer is not yet. It's interesting the definition you put together around no regrets events or no regrets actions. Personally, that would be really important, I think, for frontline engineers. A statement like that as a generalization is nice, but in terms of actually having a compendium of responses that you can do, there isn't one yet. There should be. The interesting thing is that there are some very low-cost things that can be done that have huge, huge benefits. And there's a lot of examples of that. So it's a good point and it's a good idea.
Okay, we're going to wrap up the questions for this session. I know we have some questions from the web participants. However, due to our time frame, we need to move on. So with that said, we're going to move on to our next presenter, who is Koji Sakai, professor at Kagawa University, and he will be speaking on essentially, what does concrete sustainability mean? While we're changing over to the next presentation, the questions that are being captured from the webinar portion, we will be readdressing those questions perhaps when they come up in the panel discussion, because several of them are quite excellent questions, and I think all of us should like to hear them and also see how they would be answered by our panelists.
Okay, my title is the essentially, what does concrete sustainability mean? So there are some conflicts when we say what is the sustainability. So I'm trying to indicate one part of that. So this is the definition of sustainability by ISO Guide 82, which is the state of the global system, which include environmental, social, and economic subsystems, in which the needs of the present are met without compromising the ability of the future generation to meet their own needs. This part comes from the Brundtland report, as Landy mentioned. So this is the definition. So we have the global system, consists of the environmental, social, economic subsystem. So how to deal with that? So let me first mention, always, and I talked about that, the history of the Earth. The Earth was born 4.6 billion years, and then the life has evolved for 4 billion years, changing. The origin of the modern humans was born just 100,000 years ago, or so long time ago. The agricultural revolution occurred 10,000 years ago, and industrial revolution occurred just 250 years ago. And modern cement was invented in 1824 in the UK, and sustainable development was defined in 1987. It's quite recent things then. And 1997 we had a Kyoto Protocol. It was adopted and entered into force in 2005. This year is the last year of this Kyoto Protocol. But as you may know, that the US didn't ratify this protocol, and I believe that Canada recently withdrew from this protocol. But it is interesting to think of that the lifespan of the sun will be 5 billion years. So they burn out. So what happened then? This is the situation then. Let's see the change of the world population. Roman period, just 200 million. Right now, 7 billion. In the future, more than 9 billion. It means that we have the drastic increase of resources, energy, and food consumption. So if you look at the resource consumption, the population in development country in which most of the natural resources are consumed is only 1 billion, the people. So it's amazing. From that point of view, in order for the remaining people to be able to consume the same amount of natural resources as in developed country, we need more than 10 times the current natural resources, which means that the world population becomes 61 billion people. So it's a serious situation. And the causes of the climate change in the Earth, there are several reasons. I'm not going to get into the detail, but we can say that there is the carbon recycling, carbon dioxide gas to carbon fixation by natural phenomena long time ago. And right now, the fixed carbon to the carbon dioxide gas by ourselves, which means that the global warming is caused. There are some people who who don't believe the global warming. Still, there are many people thinking in such a way. Well, let me show that very simple data of the planets in the solar system. There is the Sun, Mercury, Venus, Earth, Mars. So the temperature of the Mercury average is just 167 degrees, which is the nearest planet to the Sun. But if you look at the Venus, this planet has the 464 degrees Celsius. Why? Because the atmosphere of the Venus is almost carbon dioxide, 90–60%. So that we can say that the global greenhouse gas due to the increasing carbon dioxide is so evident. Of course, we don't know exactly how much it will affect us in the future. So this is the fact, which I know that. Let me talk about the natures of the concrete industry, which is the essentially local industry. Concrete structures are built by local people by using local materials. And the component of the material of the concrete are very simple: aggregate, cement, water, and some other, including admixture. So the concrete made from the most abundant substances on the earth. That's the reason why its production has been able to expand to respond to the growing construction demand. And the concrete, as you may know, that concrete is the second most consumed substances on earth after water, more than 20 billion tons. I would say that 25 billion tons. And then we can say that contemporary society cannot exist without concrete. It's quite obvious. So development of a nation is directly correlated to its consumption of concrete, which means that increase of the construction investment. This is the world cement and steel production compared with the GDP per capita. Purple color shows the GDP per capita, and blue one is the cement production. And green one is the steel production. So you can see that in order to get the GDP per capita, we need the cement production, cement and steel. This figure shows such a phenomenon. And this is also the per capita GDP and construction investment in major country. So these are proportional, which means that it is very important to invest for construction to have the wealthy. CO2 emission source in the concrete industry, there are several things: that material manufacture, concrete manufacture, execution, repair and strengthening, and also demolition, recycling. At each stage that we have the transportation. So this is the world cement production in 2017. The total number is 3.6 billion tons. But you can see that China, 57.3%, almost 60% cement is being produced in China. How about steel? Steel is the almost same. China, 45%. So this is the current situation. As you may know, that India has the almost same population as in China. So in the future, the both big countries started consuming both the materials. So what happened? CO2 emission in the concrete industry, concrete and construction industry, I roughly calculated from the concrete industry, we are emitting 5 billion tons CO2, and construction industry 6.3 billion tons. So this number may be a conservative. In the future, if it is to become doubles, 10 billion tons, concrete industry and construction industry 12.6 billion tons. This is the my calculation, rough calculation. So problems, what are the problems of the concrete from sustainability's point of view? Inadequate safety of concrete structures to unforeseen external force. How to set safety factor of materials, external forces, and others in design. So this is the point which we have to discuss today. And the second point is the enormous consumption of natural resources. How to reduce it? And third point is the generation of a large amount of the CO2 in cement and steel productions and construction works. How to reduce it? This is the point. Let me see that Japan disaster, March 11 last year. There was the tsunami, and this is the situation after the tsunami and earthquakes. There are some reinforced concrete structures are remaining, and this is the quite clear. Only the concrete structures remaining, and wooden house has gone completely. So what are the lessons from the Japan disaster? We can say that without robust infrastructures and houses, buildings, human society has no chance of sustainability, which consists of environmental aspect, economic aspect, social aspect. Let's see the environmental issues that due to this earthquake and tsunami, cluster deformation changes natural environment, which means that nature destroyed nature. And a huge amount of rubble were generated. And also a huge amount of the resources, energy are necessary to rebuild infrastructures and houses and buildings. And radioactive contamination occurred in some regions. How about economic issues? The economic activity in the region totally collapsed. And many people lost their job and therefore income. And a huge amount of the investment is necessary to reconstruct the region. 20 trillion yen is expected. And also we need to clean up radioactive contamination. It takes some time. And how about social activity, social issues? There was almost 20,000 victims. And many people lost their homes, and many jobs were lost. And long-term evacuation of the local population is expected due to radioactive contamination. So what is the essence of this sustainability? The destruction of social infrastructure and facilities exert a laser negative impact on economic and social activities. And on the other hand, the simple expansion of the economic activity using the infrastructures which we construct is not desirable from a sustainability perspective. The balance among the enhancement and resource and energy efficiency and the economic growth and safety society is our ultimate goal, which is the essence of sustainability. What do we need to consider as environmental aspect? So the evaluation system, we need evaluation system, environmental impact assessment system, LCA, and we are developing ISO standard. Also we have the evaluation tools, including LEED, CASB, Iridium, etc. And this is the life cycle flow chart. In the past we are thinking cradle to grave, but nowadays we need to consider cradle to cradle by recycling. And object of the environmental impact assessment in LCA, there are many aspects: global climate change, natural resources use, and others, land use, eutrophication, air pollution, and water pollution, soil contamination, etc. There are many aspects which we have to consider as the object. And there are some environmental and sustainable standards for goods and infrastructure in ISO. ISO committee, there are 3 ISO committee, technical committee, which in which the environmental or sustainability aspects are dealing. ISO TC 207, which is the environmental management, and ISO TC 59, subcommittee 14, subcommittee 17, and TC 71, subcommittee 8, which is the environmental management, for concrete and concrete structures, which I'm chairing. And this is the current member of the subcommittee 8. We have the 12 countries P member and also 10 O members as shown here. And we developed the ISO 13315. We published part 1, which is the general principles, and right now we are developing part 2, which is the system boundary and inventory data. And we are supposed to develop the remaining document. And this is the content of the part 1 and what it looks like as a document. And the ISO is saying that, advertise that after this completion, solution to environmental impact of concrete with new ISO standard. And this is the part 2, the content. It takes a little bit more time. And this is the system boundary of cement production. I'm not going to get into the detail, but all activity we need to set a properly system boundary and calculate the environmental burden. I think that remain time the 3 minutes. So I need to a quick finish there. There are many aspects. But that's why we have to consider the sustainability for the future perspective. Global population reached 7 billion. And we need to consider balance among safety, resource energy, consumption, goods, service supply, and environmental burden. Those are key in sustainability. And we can say that 3 scenarios are possible as the function of population, living standard, and resource energy efficiency. So let me skip that. I'll show you just a figure that we need to consider the reduction of the environmental burden, but increase the production of goods and service. This is the which we have to pursue in that direction. And yeah, let me go through that and the perspective towards sustainable concrete structures. Robust and resilient concrete buildings and infrastructure are the basis of the sustainability. This is a very important point. But how to balance of the safety, durability, and resilience with the environmental stewardship. This is the point which we have to discuss today. But there are a conflict among them. So the conflict, what type of the conflict there is? Let me skip that. This one. So the lateral axis shows the safety, and longitudinal axis the environmental burden. If you don't develop the new technology, if you want to increase the safety, it means that simply the environmental burden increase. But if you introduce partially the new technology, you may be able to keep the environmental burden to increase the safety. But ideal situation is the scenario 3. By increasing the safety, but environmental burden decreasing. This is what we have to aim in the future. I'll show you one example of this scenario. So this is the 2 RC rigid frame viaduct And left-hand side is the conventional one. And right-hand side, there are some new technology were introduced. And we calculate the carbon dioxide. So the new technology is introduce the carbon dioxide. We could reduce 25% in carbon dioxide. And we got the last earthquake in the East Japan Great Earthquake. So the left-hand side was the conventional one, and right-hand side is the new technology-induced the structure. There was no damage. This means that the introduction of the new technology into viaduct decreased environmental burden, CO2 and resources reduction, and also increased safety. It's going to be no damage in earthquake. So this is the ideal direction. It's quite difficult, but we need to pursue that direction. So I have a couple of this now. Durability. The how to incorporate environmental and the economic aspect into durability design. So it is very important to assess life cycle impact and the cost in durability design. In such a case that we need to introduce indices like that, as shown here. We need to develop the indices to properly assess the life cycle impact and the cost from the durability's point of view. And resilience, how to incorporate resilience into design of concrete structure. According to concrete JSI, resilience is the capability to anticipate and minimize potential destructive forces through adaptation or resistance. We need both. And this is the definition of the JS and the ASC Committee on Critical Infrastructure. Let me skip that. So concluding remarks, I would say that there are two meanings in concrete sustainability. Number one, sustainability of the concrete industry, which means that by doing the concrete industry can have the profit and also have the employment by production of the concrete and the concrete structure. This is one part of the sustainability in concrete industry. And the other part is the concrete for sustainable society, which means that low environmental burden, high safety, high durability, and high resilience. And the comprehensive method to a system to incorporate safety, durability, resilience, and environmental stewardship into design should be developed. And we need to consider safety and resilient design. How to set safety factor, how to introduce risk analysis, and how to introduce recovery systems. And also we need environmental design and durability design. So after this presentation that we have the forum, we may be able to get the some concluding remarks. Human being invented a great idea, sustainability at the end of the 20th century. From this idea, our problems have become quite clear. So concrete, I would say that there is no other alternative. We need to continue to utilize concrete. Okay, this is my presentation. Thank you very much for your attention. So let's continue the forum, and all speakers could move to the front.
Okay, we'll have the speakers move to the front, please. And at this time, we will introduce our panel discussion moderator Florian Barth, President of FBA Engineers and past President of ACI. Before we begin this portion of the Sustainability Forum, for those that are in the audience and online, there is an additional code to receive your PDH units and your GBCI credits. That code is L as in Larry, D as in dog, 4, and J as in jam. L as in Larry, D as in dog, 4, and J as in jam. With that, I'll turn it over to Florian Barth, our moderator.
Julie, thank you very much. Now, this is the participation part of the forum, so everybody needs to get active, and we will get started here shortly. They use the past president because we're a have-been, and they don't think we can't present anything anymore, so they use us for the leftover work. I'd like to welcome you to Toronto. I'm from Northern California, and to us it's the Hollywood of the North. That's where most of the work is done, if it's not done in LA, or the city in the park, which I like to think of Toronto. Toronto is the largest city in Canada and the 5th largest in North America after Mexico City, New York City, Los Angeles, and Canada. And I thought that's a fun fact. That's quite a large metropolitan. It so happened to be one of my favorite cities. If you had any trouble at the customs or got a little slowdown, I figured out why that could have happened, because 49% of the Toronto population actually was born outside of Canada. And they probably try to keep more of those people which came in and out. The high intellectual level in Toronto is probably due to the fact that half the Toronto labor force or workforce has either a college degree or a college diploma, which is really amazing. And it's a real, you probably can tell I really love Toronto. But Toronto is the perfect city to host this forum, considering that Toronto's waterfront revitalization project is a sustainable showcase. Toronto is considered the most sustainable big city in Canada and rated 2nd among 27 global metroplexes in economics and social values. But let's start with the panel discussion, and we have our 5 speakers right here. The father of sustainability, Koji Sakai. We have Randy Poston, Mr. Code, if you want to remember that, Mr. Durability, Doc Hooten, and of course Mr. Resilience is Michael Collins, and Adaptation is Michael Mortimer. You have witnessed 5 well-rounded and very informative presentations which addressed issues our industry faces. I would like to give a round of applause to our speakers. The guiding principle of this discussion when it comes to sustainability, I like to refer back to George Box's statistician, which said all models are wrong, but some are useful. So with that in mind, we like to think about what we learned from these presentation, and it clearly gave us a point that while we need to continue to work and make an effort to minimize climate change, data clearly indicates today, and some of you may have seen some of the data in very publicly distributed documents, that it is no longer avoiding climate change, it is no longer minimize climate change, it is really what Michael said, adapting to climate change. Some say the most sustainable structure is the one never built. We as designers like to say it's the one never built twice. The building is still standing, and hopefully the bridge is still in service. LEED Platinum rated today and flat tomorrow is not a sustainable structure. With this, we selected 5 topics. We take general topics, and then use those topics to field our questions. I'd like to start with our first topic, which is concrete is used to make communities resilient through buildings, dams, bridges, and accessways. Are we doing enough to respond to the rapidly changing climate? And I'd like to add to this that if some of you have read the National Geographic September issue, which had great graphs showing from 1920 to today the rapid climate change, whether it is wind, water, fire. And if you look at those graphs, it is shocking because they are spiked so drastically in the last 10, 15 years that designers always based the design values on historical data. And I don't know how we can use historical data with such rapidly changing climate environment in the future. I'd like to point that to Randy and maybe Michael to see how to handle this going forward, because the data pool, you can no longer take a statistical average or means going forward. Randy? Mr. Code.
Mr. Code. Well, we, at the conclusion of presentation, asked the question about really geared towards resiliency, and certainly I found the presentation by Michael Collins most interesting about looking at a community that, although may have been designed to meet modern building codes at the time, certainly may not have fared quite as anticipated. So this concept of what building code should be, what specifications should be, I think has to change. And I'm not smart enough to know exactly what all those means, but certainly some of the ideas too that Michael Mortimer talked about with probabilistic and risk-based methods are certainly something that need to be introduced. I know in the United States we're still very much deterministic based in terms of looking at loads and the responsive structures to those loads. I mean, there has been some attempt on the loading side with ASCE 7 load to develop the requirements, but again, there are minimum requirements for loading of structure. So, you know, perhaps what we need to do is expand our thinking about not minimum requirements, but something much more robust than that, which I think is the idea of resiliency in the code that a number of speakers have talked about.
I'd like to field one other question to Michael Collins, and that is there are three stakeholders when it comes to resilient or structures which don't perform. And those stakeholders are obviously the owner of the structure of the building, government by default, because the FEMA has to come in and spend money to rebuild or help rebuild. And of course, the third stakeholder is the insurance industry. Now, the insurance industry in the U.S. has done some testing, and you may be aware of the fortified system which they have proposed, which is above code. But what do you think is the right way to address this? Is it through the insurance carrier, the largest stakeholder, or what would be the right avenue?
Well, you won't get much agreement in Christchurch that we'll leave it to the insurance companies. Even though New Zealand has an unusual system because of the Napier quake, after which a lot of insurance companies said that was an act of God, we don't cover acts of God. The government of New Zealand passed a law saying if you wish to write insurance in New Zealand, you must cover earthquake risk. And to make that more feasible, the government set up a program to basically cover the deductible. So all insurance premiums had a premium on top of the premium that pay into a government earthquake commission. That government earthquake commission had about $5 billion at its disposal when the Christchurch quake hit. Unfortunately, the damage in the Christchurch quake was $30 billion, making it, I believe, the largest reinsurance event ever because everybody was insured. Whereas in California, if you have a big quake and San Francisco is destroyed, probably a lot of the building owners will not be carrying insurance because the deductibles are so large.
That's correct.
I don't know that the insurance industry is the answer. I mean, what a lot of building owners in Christchurch said to their engineers, you didn't tell me that if a big earthquake hit, I was going to have to demolish my building. And there are buildings over there that are standing and are operational. And the structural engineers say, well, of course, if you had been prepared to spend 1% more on your building, it would still be standing. And they said, yeah, but you didn't give me the choice. And I think we have to hope that we can educate the owners of important structures that it is, in fact, a wise investment. And I think we have to rely upon innovative engineering. And if people put half as much ingenuity into designing the building as they put into trying to avoid liability for something going wrong, there would be no problem solving these issues.
I'd like to add that this is also the time for our online webinar participants to please field questions, and Julie will be the one transferring them to us.
One of the questions that's come that's very similar under this topic is, I believe we were talking earlier about loads, Mr. Poston, and it was talking about, you know, we need to maybe reconsider how we look at loads. Should we be anticipating or should we be designing with climate adaptation when we start looking at loads and how we should be designing for loads?
Just to make it clear, I'm not Mr. Poston, I'm Mr. Building Code.
Mr. Building, I'm sorry, Mr. Building Code.
It worked.
Yes.
Yes.
Yes, I mean, I think it's a chicken and the egg kind of problem, I think, in terms of expressing what forces need to be designed for, and a lot of it is, you know, we don't want to see ourselves going back to the mode of trying to design a structure to remain completely elastic. We need to provide mechanisms within the structure itself to help accommodate these types of movements associated with forces and so forth. And the adaptation component of it is something that, yes, I think we can make some transition to that area, but it's going to take some thinking about what the load, what the load response of the structure may be under the adaptive forces. And again, frankly, until today, hadn't given it a whole lot of thought. But I think there's real opportunity to take advantage of that to make a structure more resilient.
Okay.
Colette, you had a question?
We also have one other comment from Michael Mortimer on that same question from the internet. Sorry to interrupt.
Michael, Colette, if you can just hold on 1 second. Michael, why don't you?
Yeah, just to build on what Randy is saying, and the question specifically in terms of should building codes be addressing climate change. So I'll give a perspective on what's happening in Canada. The Part 4 Standing Committee for Structural Design that's responsible for structural design in the National Model Code for about 4 or 5 years has had a task force on climate change. And really, it's all about impacts of increasingly uncertain things. Snow loads is a particularly important concern in our geography, and how, you know, how snow loads are shifting and whatnot. And clearly, that has a very large factor on structural design. So they actually are already are addressing some of the loads that are really critically important. In terms of other codes beyond building codes, when you look at the electrical transmission industry in Canada, that is privately held. There is no public code for transmission lines. But CSA does have a lot of standards that are proxies for codes in that area, and quite frankly, they've been doing R&D on their own in this area for quite frankly, even before the ice storm in '98. So whether they don't, and by the way, in most cases, in most industrial sectors where you've got built infrastructure, they don't label it climate change adaptation.
All right, Khaled?
Yeah, I'm Khaled Awad from ACTS Lebanon. I was involved in the...
Doesn't look like the speakers were. Can you just speak up?
I was involved in the development of a zero carbon city, trying to make it sustainable. And one of the major challenges when we went into the designing of the structures in the city was the procurement model based on initial cost. You've mentioned, Mr. Collins, the 1% additional cost that you would have if the owner had the choice. You would have taken that 1%. Most of the procurement today is based on initial cost, initial capital cost. And we keep on talking about life cycle costs. This is in life cycle analysis. Who is responsible among the, whether it's the standard code or the building code, the standard association of the building code, to drive the procurement model into life cycle cost procurement, because this is the change that can really make an effect on our structures in the future.
Yeah, it's and you see what FIB has done. The responsibility has been essentially placed on the designer, the design professionals, for doing that life cycle cost analysis, and it's a big burden. And you know, the thing about professional services and engineering is that it takes more and more money in order to do some of these things, and of course owners are not willing to pay for it. So how do we resolve that thing? It's a very, very difficult problem.
Okay, we're going back to a online question.
Yes, I think this lends to similar kind of questioning. It says contractors and concrete suppliers are also interested in the initial and the first construction costs, thus gaining money in these stages, so we need policies. And if so, how would we enact these policies within society and within direct governmental policy? Do any of you have any suggestions?
Sounds like more regulation. I'd let Kochi maybe respond to that.
Yes, Floria mentioned that this is the regulation problem. If you have the regulation in which that you require some such things that the people have to obey that. So without having any regulation, it doesn't function. So I think that the most important part to consider the life cycle cost and life cycle assessment is that we have the requirement by owners. Yeah.
Michael Mortimer wants to also add to this.
Yeah, that's yeah. It's can you hear me? Okay. Okay. Yeah, that's actually an excellent question, and maybe I'm going to be the contrarian here. Although, as a somebody who's as a standards nerd and somebody who relies on my standards being referenced in regulation, I want to also point out that's not the only policy instrument that we have. U.S. Green Building Council LEED and no, that's not about adaptation, I realize, but that wasn't regulatory driven. That's very much an example of a market driven policy driver getting us toward better than minimum codes. So regulation, absolutely a very powerful policy instrument, but it's not the only one to raise all boats. Certainly market driven has also. There's other types of incentives, and we'll get back to the property and casualty insurers. Whether there's regulations or not, as it was pointed out, okay, these companies are in business to make money, not to lose money. So although it's a negative incentive, de-insurance or exclusions in insurance is a huge incentive. One example, very small example, if you look at Hurricane Andrew that went through Florida in the early 1990s, some very, very inexpensive fixes, whether it was hurricane clips to keep roofs on or hurricane shutters, that type of thing, could have saved literally millions, if not billions of dollars, okay? Now, eventually that did lead to a code upgrade, but as insurance, I can tell you right now that the property and casualty insurance world is very concerned about the impacts of climate change, and they really don't care what is causing it. And those incentives, whether they're positive incentives or negative incentives, are here now and will be coming. And the insurance industry is doing a lot of research in how they can, if the codes won't and the regulators won't put these things in to raise all boats, I can guarantee you that the insurance industry will.
Yeah, and that IPHS is doing that through independent testing, and that testing hopefully will result in some form of benefits to the insured by getting credits.
I'd also like to add a comment on that. Most recently, the NRMCA took on an initiative to actually speak to government, stating that if we can build beyond code originally, that we save millions of dollars when things actually have catastrophic failure. So presently right now that they have a bill going before the House that would say that if, along with the IBHS, that if you would build above code after a disaster has occurred, a natural disaster, that you would be afforded the builder, now we know the builder sometimes changed codes, but the builder, if he would build beyond to a code plus, would be rewarded tax credits. So there are things going on within the industry to try to help promote these code plus issues as well.
I'd like to field another question here from an attendee. Can we get that microphone working, Kevin? Because you will be Kumar will not.
I would like to respond to your question. Are we doing enough to respond to the rapidly changing climate condition? This is a question addressed to each of the panelists. In my opinion, I have attended all the forums, sustainability forums, and what I miss is the lack of urgency of action. We are not doing fast enough. And the example I want to give you is some of the data shown by Professor Koji here. The speed at which the carbon emissions are going up, the intergovernmental panels plot which you have seen, they are now growing up exponentially. And I was interested to look at it, how much our industry is responsible. And since, as one of the panelists has given us information that the concrete industry's carbon emissions are mostly attributable to Portland cement production and consumption. If you look at the total production of Portland cement during the last 10 years or 20 years, it has also growing up exponentially in the same way. So 10 years ago, it took us 8 years or so to increase the growth of cement industry by 500 million tons a year. And now last 2-3 years, it is only taking 2 years. So there's a similar exponential growth of cement and concrete industry going on. And probably it is due to single-handedly by China, but we are now a global village, the whole earth. So whatever is happening to control the carbon emissions in other countries is having a very high effect by the contributions from China. And what can we do about it? So I think the data from the climate scientists show that we do not have much time left before the climate change will become completely irreversible phenomena. And if that happens, and the number of years they cite is anywhere from 15 years to 25 years or so, which is not much time to take action to have control on the carbon emission, to stabilize them or bring them down. So my concern is that you are still lost in how to change the codes and how to do this, how to do that. And most of these changes are motivated either by immediate profitability, economic considerations, or the political considerations. So nobody is interested in the environmental stewardship. That is just an empty phrase. The balancing of it does not make any sense, because without the stewardship of the environment, the survival of the human society on this earth is not possible. So given this kind of urgency, and I have the data to show to you about the milestones in the climate change and other things about the cement production, concrete production, last 10 years and 20 years. And you will be amazed to see that the cement and concrete industry is growing at the same exponential rate as the carbon emissions of the world. So each of the panelists, could you please respond? We are not doing it fast enough, and the age of denial is long gone. Thank you.
I think some of that was addressed by Kochi's presentation, and it is not even prorated yet, because you made the point, and I forgot the numbers, but you made the point that developed countries create a certain amount, and it is very likely as the rest of the world develops, it is a multiple of what you even are concerned about. So it is actually in two-direction exponential. But I don't want to take away. Why don't we start maybe with Kochi and go if some have comments.
First of all, I would say that we cannot estimate our future exactly. This is very important, but we can calculate roughly what's happening in the future if you consider the current situation and the consumption of the energy. And then it seems to me, as I showed in my slide, as you mentioned, that the situation will become quite serious. This is my understanding.
Thanks for the question, and I'll key in on that there doesn't seem to be there isn't any urgency, and the rate that we're changing is too slow, and time is running out. I just want to keep reminding you that this isn't something that's happening in the future, it's happening now. If you look at the circumpolar regions north of the 60th parallel, okay, the rate of warming is happening about 2 or 3 times the rate of what even the most conservative climate models are predicting. So it's there now. This isn't an esoteric or academic argument. So that's one area where there is no other options. Adaptation is the only option. The other reason it's not top of mind perhaps with you know, the average person on the street is, that if you look, for example, in Canada, across all of the north, you have a population of 100,000 people maybe in hundreds of communities, and primarily in 2 or 3. Other circumpolar regions, by the way, are in exactly the same boat. Now, let's go to the other extreme, where other parts of the world that are living climate change impacts right now, but are perhaps at the other end of the spectrum of economic resource. Singapore comes to mind. Although Singapore, it's an island city-state, although it doesn't have any natural resources of its own, it's a highly, highly educated population. The per capita wealth in Singapore is very, very high. And without going into a lot of detail, they take both climate change mitigation very seriously and adaptation. They have no choice. All right, and if you want to look at a model of an area of the world that not only is addressing it but doing it very quickly, look at what Singapore is doing. You know, they've got they're probably decades ahead of some of the major cities, even in Canada, the U.S., in terms of cooling zones that don't necessarily rely on air conditioning. And there's a lot of very, very innovative adaptive responses going on. So my key point is, it's not about the future, it is about now.
Of course, Professor Mehta brings up some very good points, and he has brought concerns before us all a number of times over the past decades. The trouble is, human beings are very bad with dealing with things that aren't happening right now, and they're very bad at dealing with things which seem to have a small possibility of occurring, but if they do, will be really terrible. And so we're sort of fighting human nature. And what we see so strongly in Christchurch is human lifespan is so small in geological lifespan. And we're very good at dealing with things that happen every few years. We're not so good at dealing with things that happen every generation, once every 25 years or 30 years. And we're really terrible at dealing with things that are even lower risks than that. And it's not just CO2 we have to worry about, of course. You know, that's just one of the many greenhouse gases. So I have no doubt that the climate is changing, and that's a whole philosophical question on its own, but we should be doing a better job. I'm a structural engineer, so what I look at is what should my profession be doing to contribute to the health and good of society, and so that future generations will live well. And I worry in this city that I've called home for 43 years, when I look at all those high-rise buildings that have been built, and an awful lot of them are condominiums. And talk about the owners, well, the developers who build them are the owners for a little while, but then when everyone buys their condo, they become the owners. And so the developers have very little interest in spending more money, which is going to pay back longer term. And unfortunately, the developers, at least in this legal environment, often set up some numbered corporation, which is the company that owns it when they build it, and then after that, it's the owners. And they spend all their money on granite countertops in the kitchens, because that's what people see and buy. And they spend very little money on improving the resilience, for example, of the structure. And God forbid that something really nasty happens. When I drive into work each day and watch all these constructions, I think, I'm glad I don't live in that one. I'm glad I don't live in that one, right? So there are a lot of substandard, no, not substandard. They all meet the standard. That's the trouble. You know? We have this belief that if it meets the standard, it must be acceptable. But that's not good enough.
Michael, we have a long list of online participants and a lot of questions. So if, Doug, you want to just give a real short comment?
Just to address the urgency thing, some of these things way beyond our control. We can do things to improve the sustainability of things we build, but the number of things we build and the quantity of materials used is directly related to the population of the world. And unless we get population control under control, and you can see in Koji's presentation the acceleration of population growth, and the more people there are, the more things they need. You build things. And so until that's dealt with, I don't think some of these things are way beyond our control in terms of regulation or improvements.
I think my only comment is I think to make kind of leap-bound jumps in this, we are dealing so far with conventional materials in cement, steel, and water. The reason we use concrete is because it's a very inexpensive material. If you want to limit some of these other things, I think you have to have pretty advances in other types of materials. But guess what? Those are going to cost more money. So there's back to the economic factor in all of this. It's a very difficult problem.
Yeah, I think this issue is definitely looking at it from the 30,000-foot level and needs to be addressed. But we have quite a number of questions. I'd like to move on to the next question. Julie.
Before that, I just have one comment. You also talked about manufacturing of cement and cementitious materials. And I think it's very important for this audience to understand that everything is being done within the industry. As an industry representative, I can tell you that we have very high standards in place to reduce all that we do on the environment, as well as trying to find things like alternative fuel sources, alternative raw materials. And somewhat of what it concerns me that somewhat of the ways that you look at it is somewhat a misnomer. We have several plants that run on 100% alternative fuels. We run on waste gases that come off of landfills. So
not every country has those standards.
So everybody has those standards, but the World Building Council Sustainability Initiative with cement.
They're trying to accomplish that. They're now having a protocol for plants in India and China to abide by some more stringent requirements.
Correct. Okay, moving on. One of the questions that was put forth is how can ACI support researchers or engineers in other countries to convince the society and policymakers to notify the importance of sustainable and resilience concerns?
I think through our international partners, we have a great network of international partners, and we have used the international partnerships through exchanging publications, and I think there could be more done in that direction. But if any of the panelists want to add comment or response to that? We'll go on to another question. Any other question here in the room? We'll take another online question.
It seems that the concrete industry is as important as the defense industry for many countries. How can it be explained to government or administrators of provinces, regions, or countries how important this issue is? Are there tools available for us to do this?
Any comments? Michael, do you want to address that?
I think that it doesn't matter what sector it is, whether it's the concrete industry sector or many of the other sectors within construction. Many of the industry associations are, part of their role is to actively advocate not only on behalf of their members, but also to educate elected officials and other policymakers on how, not only on what they are doing in terms of responding to sustainability issues, whether they're environmental or economic or social, but also to help to educate policymakers. And I think in the from the outside looking in, certainly what I've seen in the concrete sector, both in Canada and the United States, you do actually have very effective industry associations that are working to put out educational tools. certainly organizations such as ours can also help in terms of that general overall education.
I'd like to switch to the discussion topic number 2, how to deal with the redundancy to safety and durability of concrete structures for sustainability of society. Is really to get the infrastructure more redundant, and that very much links into Michael Collins' presentation, and I would like your input on how do you see to provide redundancy that we do have an infrastructure which is at least functional after an event, whether it is seismic or other climate loading.
Well, I think it's partly trying to use innovative engineering and look at cost benefits of different improvements that one can postulate for a given structure. And there's not going to be one answer for everything, but given any project that has to be designed, such as the viaduct that Koji was showing us, then the question is the attitude of mind of the engineer that goes in. Does the engineer see his or her job as simply meeting a set of minimum standards and just making sure that under the 30-year windstorm the structure has less than a certain acceleration on the top floor? Or do they also have in mind what happens if there's something way beyond what I'm considering? Can I do something so the structure will still behave reasonably well? And they're very hard to codify those things, but I think what we have to do is raise the prestige of the engineering community in North America by people appreciating that this isn't a commodity and you shouldn't be purchasing your engineering services based on the lowest bid. And until we can get out of that mindset, I don't know that we can really have an answer to this.
Yeah, it's the first time in my lifetime that USGBC managed to do something on a voluntary basis which actually cost more. So there must be a model which could work, but I'm not sure exactly what that model would be. Yeah, you had a comment.
As I indicated in my PowerPoint, this is very important. It seems to me, I would say that we haven't discussed about that seriously. Of course, we have the safety factor in the design of the concrete structure, but we experienced the magnitude 9 earthquake. Fortunately, we didn't have the serious damage in the structure, the concrete structure, but in the future, there is a possibility that we may have the more big earthquake. So at least we need to consider if we change the safety factor from 1.2 or to 1.4, what is affected economically and environmentally and socially. So all factors should be considered by evaluating quantitatively by using our knowledge. That's what the reason why I indicated in my slide.
Any questions, please? Kevin.
Yeah, it seems to me that in listening to this discussion, there's a conflict between sustainability and I got my terminology wrong, but
resilience.
Yeah, and basically the issue is if you increase the safety codes, the response of most engineers, and this is the point you were just hitting on, is to just add more steel and more concrete. There is very little innovative engineering that goes on on a day-to-day basis to reduce the amount of concrete that's required to achieve the same end or a higher standard. And really the response of the industry, the engineering industry, has to be better engineers. It's just not good enough to say, well, here's something we've been doing for 45 years. I didn't design it. I probably don't even really understand it. But I know if I add more steel and concrete to it, it's going to be stronger. And that's not good enough, because you may make that structure last longer, but when you look at the sustainability issue, you've at the same time consumed more durable goods, more CO2 added to the atmosphere, and your sustainability is at odds with increasing your life cycle of that particular structure. And so I think the industry has to take responsibility to sharpen their pencils and get back to what the industry is all about, and that's a design.
That was more of a comment than a question.
I would like to advance on that.
I do agree with that. And just as a sideline, I like to point out that the Concrete Joint Sustainability Initiative has defined or tried to define how resilience works into sustainability. And we looked at green plus resilience. Resilient is or equals sustainable. So resilience has to be part of a sustainable structure. Now, you may operate and get local materials, which is the green part, but you have to have ultimately a resilient structure to have a resilient and lasting infrastructure. So I think there are some clarity for how resilient fits into it. But somebody wants to respond to the that engineers need to be more innovative. I think we probably all agree with you. Yeah. Julie?
There's a couple of questions I'm going to kind of push into one question, and it says that, you know, there seems to be many technologies that are available within the concreting industry. Examples of like SEMs, of polymers such as FRP, but they're slow to be adopted. How can we help to get them adopted more worldwide to help with the sustainability of concrete and engineering practice?
This is an online question, and Randy, do you want to address that, Mr. Coate?
I'll certainly try to give a few comments on it. And you know, the nature of being engineers and what we do, we tend to be fairly conservative, and we do get into this mindset of tending to go down the same path that we've always gone. So there has to be a paradigm shift in how we think about design. But again, I think some of it is the adaptation of new materials that are out there, FRP being one of them. But when you look at the you know, it gets down to the reality of the benefits cost to some of these items that are being used. The owner can be a public agency, public works, so for infrastructure, or it can be private concerns, has to be frankly willing to pay for it. And and that's where I disagree that it's all about engineering. I mean, yes, we have a job to do, but the reality is there's only a certain amount of that we're allowed to do with our skills. There has to be an interconnection between what is not only desired by the owner, by society in general, along with some of that engineering that's done. So it's slow to adapt. We have made, certainly Temps ACI has been very good. We have a document, for example, on FRPs, but fundamentally it gets back to, you know, the reason I said before, we use concrete as a very magical material, and it doesn't cost a whole lot of money when you think about it per pound. And it's hard. I don't know what material out there looming that you're going to be able to replace it with.
I'd like to take another question from the floor. Yes.
Thank you very much. I just wanted to kind of answer on the last question on innovation. There's no way we can ever achieve improve innovation until we get the media and government to highlight success. And you know, your presentation, Michael, on the Christchurch was a perfect example. The media really only looks at that which collapses. We, in the industry, I get all of the smart briefs, and we highlight amazing buildings that are resilient and innovative. But the media and the public, they don't. They only look at failures. So in order to really drive the industry to become more innovative, if there's anything we in the American Concrete Institute can do to influence government to perhaps recognize structures that are done well, innovative, low material, that's the key to drive innovation. I apologize for this feedback on this microphone.
Yeah, we talked earlier, as engineer, I have to also say, we talked earlier about what we could do to get more regulation to force the life cycle part of sustainability into the design. And regulation is one of the items which we all face and ties our hands rather tight. But any comments to the last question from the panel, whether we really need to do better job in highlighting our success stories? Looks like there's agreement. So Julie, we'll go to the next online question.
Okay, this comes similar. It's kind of a similar question. It says it's actually twofold. In developing countries, we have problems just reaching 25 MPa at 28 days concrete strength, and we need more sustainable concrete. What is the solution in educating in those types of countries? And then I want to put a two-part onto this because it comes back to, we've talked a lot about the designers. What about those of us that are contractors? How can we be better educated so we can implement more of the sustainable practices that you've discussed today? And how is it done in other countries, since you have a vast array of panelists here?
I'll let the panelists respond to it, but I certainly can say that when I looked at some of my material which I worked on 10 years ago, and it's so obsolete, it is unbelievable. And I don't think we're anywhere near an equilibrium. I think we're still on the, not even cutting edge, but the bleeding edge of sustainability, and have so many unanswered questions. So it is a total evolution. Julie, you know, at the Concrete Joint Sustainability Initiative, every meeting we meet, and that's 4 times a year, there's a new, or 1 or 2 new organizations pop out of the ground with new ideas and new directions, and we try to catch up. So any other comments to this question?
I think the comment about contractors was interesting. I've certainly seen in even our area in Texas that you know, contractors are beginning to expand their thinking when they go into a project of what other whether they can take existing materials and use recycled materials like they've done at the Toronto airport. They're looking for any advantage they can, recycling, reinforcing steel, all those sorts of things that give them, frankly, an economic advantage, but by doing so, it becomes a sustainable type of operation.
And the first step, of course, is awareness. I'm really was surprised to see that a lot of the contractors in California, almost every project manager is LEED rated. So it is just, the first step is always knowledge, being aware of what you can do or what you could do or where the hot spots are. But the second step, of course, is implementing it. Any other? Please go ahead.
Thank you. I agree 100% with what that gentleman said there. I'm a design-build contractor. I have my own engineering company. I work across Canada. And one of my pet peeves has always been over-design. As a young engineer all the way through my career. And we're trying to take leadership by coming up with an audit system internally. And so what we do is we rate our designs. We have our own calculator. And I'm trying to come up with something leaner than life cycle analysis, because that's very expensive. All the consultants are embracing that and charging a lot of money to administer it in a precise way. I don't necessarily agree that durability is the single focus. We've got to try and reduce the amount of materials being used here. The cement industry may not like that, but if we can reduce materials, then we can buy innovation time. And if we have innovation time, engineers will solve the problem. It is an engineering problem, I feel. So what we're doing is we're auditing. And my question to the panel is, if we're auditing internally, my thought is would not make sense for us to contribute to a nonprofit that audits engineers and creates the mindfulness that the one gentleman talked about. In Ontario, the regulations say you can't criticize another engineer. Now, criticizing, my thought is you come up with a scoring system that the government start to respect, where when it's properly audited, they'd be given some consideration for those awards. Governments currently in Canada are awarding to large engineering houses whose standard of soft costs have gone up, and if the slab's thicker, it allows them to bill more. I can tell you 2 projects in Toronto, if you want to see me later, that have wasted up to $50 million, and our governments can't afford it. So what do you say about auditing engineers to create mindfulness in a way that doesn't necessarily penalize them, although if it's made public, then maybe we'll create mindfulness of those scores.
Go ahead, Michael.
Could I just give one cautionary example of scoring engineers? In the concrete offshore business, innovative designs of concrete platforms were, in Norway, a fantastic achievement. When the discipline got to a certain level of maturity, the particular innovative company was bought by a bigger company, and that bigger company bought into the American myth that you have to have a number on anything before you can evaluate it. And they said, how can we evaluate the quality of the engineer? And they decided to come up with what they called the utilization factor. And so for each engineering that they did, they'd see what percentage of code allowable did they reach. If you had everything up to 100%, you had a utilization of 100%. And they gave the engineers bonuses depending upon how high the utilization numbers were. The first platform they designed under that system was the only concrete platform to fail. It was the Schleipner platform. They got wonderful utilization factors. They produced a non-resilient structure. So my caution is, it is very hard to quantify in a simple thing that a lot of people can comprehend the quality of engineering. That's my caution. I'm not against what you say. It's wonderful that you're scoring yourself internally, but I'd be very cautious about trying to promote some sort of general scoring system of engineers. It would be very hard not to give. And as soon as you set up a system, then people will game the system. And that's exactly what those young engineers did. They then spent all their effort working out how they could get the utilization factor up instead of thinking about how the structures might perform. They took out 70,000 tons of steel, which has saved quite a bit of money, but it was about $1 billion failure.
Very interesting approach, though. Maybe we can discuss that after the panel. Julie, we have another online.
It came in response to actually your question, and the question was, if we are to rate design communities, should we also be rating construction communities and those people that build? So it's a catch-22, I think. So in raising that question, you know, they would also say, should we be rating everyone that's on the job, from the contractor all the way up to the designer, and how sustainable and what sustainable practices they employ? In some countries, not in all countries.
Let me go to the third topic, and the third topic is how do we deal with the environmental burden of concrete structures, whether it is design or construction, from a sustainability point of view. Kochi, do you want to get started on this topic?
Yeah, today we heard that we had a good news from the ACI 318 that I didn't know that you were examining such a aspect. So it is very important to incorporate such aspect in design code. But it seems to me the final agreement in the 318 is very, it seems to me very reluctant to do things from the expression of the provision. So I'm just wondering if you are really going to do something. My question.
Randy, that was a question for me to coach you, but now it was handed on, so I'm sorry.
No. Well,
handed off.
Look, I think I mean, as you can tell by a lot of my responses, I've learned a lot today. I've learned a lot in the last 5.5 years, and we've only been in kind of the business of this probably within ACI for maybe 8 years or so. And so, you know, every engineering being conservative, it takes some time. But yes, I think, you know, there's going to be, my feeling is, I've certainly got some thoughts on about improvements to certainly the little modest amount of provisions that we've done in the, or set for the 314 or 31814 2014 building code, but something like environmental factors. You know, I'm not sure exactly how that might be introduced. I think in our system we have to get something to do something. And so it seems like it's the credit debit society that we live in, and so I think you know, it's another case where we need to be careful if we are looking for credits. Is the debit really worth it? And you know, it's a question I can't answer here today, but certainly we'll give some thought to, and certainly pass some of the general notions of this on to the future committees. But it's you know, something related to the environmental factors and ACI may be a difficult thing to do in the near term.
I think that it is a great step as ACI. There is no doubt about that. Mm-hmm. But the next step is to consider how to evaluate, to do things. Mm-hmm. That is the next step, I think.
ACI never said we're idling. We're just slow. Big difference. Michael, real quick, and we'd like to take a question from the floor right after.
I'll just make a very quick comment, and again, it's from somebody that's outside of the concrete industry, and this should give you some comfort. Any response, just bear in mind that there's no response that is environmental footprint free. Anything and everything that's put forward has a footprint. And it really, you know, be careful how you look at and how you define even the word burden. Because in every circumstance, even with your current emissions, that's a bit of a misnomer.
Okay, we'll take another question from the floor, please.
Good afternoon. My name is Reze Farhan. I'm a professor at UT Austin. We always hear about, you know, sustainability. We want to design our buildings to last for longer, be more durable. But buildings sometimes have to come down, so they need to be designed also for deconstruction purposes. So I want to know what is going on within the design community with regards to looking at how we can actually design a building for deconstruction and have that be part of sustainability initiatives.
Well, rather than deconstruction, we should consider recommissioning. So if you have a structure, let's say, which is designed today for an office building, and it has the potential to become retail or a parking structure, in the original design, the engineering team or the design team should consider a recommissioning of that structure, so we don't have this large, you know, deconstruction and reconstruction environmental footprint and minimize it. So a lot of structures, obviously, concrete is very different to many structures. The life cycle of a structure can easily we know the technology today to do 100, 200, 300-year structures. What's interesting, I just saw a statistic that the average life cycle of a structure in the U.S. is somewhere in the between 35 and 40 years, which is shocking. Where in comparison to Europe, Switzerland is somewhere in the 250 to 300-year range. A huge difference, huge different mindset. You know, we need to reuse, we need to recommission. So, but any comment from the panel, Michael?
Just to put in a gratuitous plug for CSA publications, there actually are two publications that are not widely used for reference, and one is a conceptual document on the principles of design for disassembly, and the other is a deconstructability. And if you're interested in understanding more, you can see me after. Interestingly enough, the concrete interests are not necessarily thrilled or enamored with that particular document.
Julie, do we have a online question?
There is a question here. It says, what do you think about the difference between ACI codes and standards for sustainability of buildings? Because sometimes we design, say, for a nuclear type facility versus a water tank versus another structure.
Mr. Coate, would that be something? Or do we have to go to Mr. Durability?
Yeah. Well, he's literally my right-hand man.
Your wingman.
My wingman. Yeah, I think, I mean, I've practiced in broad areas of you know, bridges and buildings and civil infrastructure, and certainly the aspect about, I think, really the exposure of those and the durability is really kind of the key factor. You know, what we anticipate, frankly, out of a building is unfortunately a lot less than what it should be, because it's all generated by the, particularly in private enterprise, by the profits that are going to be made up front more than the long term. Whereas infrastructure, there's a little more calculation about how long it should last. So, and certainly nuclear containment vessels and the like, something that we hope those last thousands of years for the most part. And it is related to the previous question. I wanted to just address that with the reconstruction idea, is that in recommissioning idea, and I've actually seen it a little bit more in bridges, where particularly when you get to more exotic type longer span bridges, I mean, there has been some effort about particularly with external post tensioning and cable stays and extra dose tendons, about how do you, recognizing that they are going to have more of a finite life than maybe the concrete elements are, and so the replacement, how do you replace those? It had really never been given any thought till 10 years ago. And so I have seen a move to where you take the base structure and you do give some forethought, at least in terms of how you replace some of those key structural elements for the future.
All right, I'll take two more questions, one from the floor and one from online. One more question from the floor. Go ahead. And Julie, if you could tee one off from online.
Hello, my name is William Wallace. I'm from Fort Worth, Texas, with Hewitt Zollers, and I'm also a member of ACI 350, which is an ACI document for the design and evaluation of environmental concrete structures. So ACI, does have a document and a committee, a robust committee that's looking into durability issues and serviceability issues that are just as important as the strength. And Mr. Poston mentioned environmental durability factors. Well, that's exactly what we do. And you do end up with a more robust structure, but that's what happens when you have to consider cracking, because that leads to the intrusion of chlorides that can attack your reinforcement. and accelerate corrosion effects. So I guess I'm here to give a little plug and a commercial for our ACI 350 committee, and I'll be willing to discuss this further with anybody during the reception. Thanks.
There's a proposal on the floor that we should design all structures as environmental structures.
Well, there can be a lot of truth to that, because I mean what I know certainly about environmental structures, and certainly have looked at a lot of cracks in them, and other ones that have performed well, and the designers knew something, particularly early on, because they limited the stresses in the bars and therefore had smaller crack widths or no cracks and so forth. So you know, it's related. It's one of those things that may not have been recognized as that per se, but in fact it did provide enhanced both serviceability and durability for those types of structures. Certainly we'll have a fairly difficult time trying to get that through 318 though.
But we joke about it, but it would be interesting to see what really the cost-benefit ratio is, because we really have no clear understanding. While the person who designs for a 350 building may not use all that much more material, but more thoughtful, and it'd be really interesting to check the cost increase.
Yeah, and this is one of the cases where I think, frankly, it's not from the strict materials performance point of view, but if you look at the structural design, and I've had the occasion to look at some underperforming water or fluid containing structures that in fact were designed by 318 and not by 350, and you find out it didn't take a whole lot to make it in order to provide for crack mitigation. It was, you know, it's a few bars here and there at a closer spacing, frankly.
I think I would make a mistake if I wouldn't have Mr. Durability say a word.
I was going to say one of the differences is time. It's not materials, but it's the amount of time you're willing to wait during the construction process. Because crack control, a lot of it has to do with controlling thermal issues, controlling shrinkage, and a lot of it involves time. Curing it, keeping insulation on so you minimize thermal gradients, all these things can help control cracks for something, because people generally get upset if nuclear power plants leak or water tanks leak or dams leak, and so they spend a lot more time, but the construction process is extended. My experience dealing with condo owners who want to go get green credits, and they want to use sustainable mixes in terms of, you know, more fly ash or more slag. The first thing that goes out the window if they get behind schedule is the sustainable mixes, because they want to strip the things at 18 hours and they want to get their reshoring out quicker, and they want to climb faster. So the sustainability is great until they have to do it and they're behind schedule. The schedule is king on a condo because they're trying to turn it over and get their money out.
I'm glad you brought that up, and you know, really, what do we save sometimes a week or two or three on a building which is supposed to last 100 or 200 years? It is somewhat counterproductive what we do today.
Well, I say to my students, I said it last week in the class, I said for the lack of 7 days moist curing on a bridge deck, you can knock 30 years off that deck, which means you're in a traffic jam. And so it's bad economy.
I'd like to ask for the last question, online question.
We're going to kind of make a joint question here. 2 parts. One, we've already looked at how we need to increase the level of safety based on current climatic conditions. But if we're going to say we're adapting to climate, we should suppose that the climate will change again, and maybe we do not have to have as high of wind loads as we do presently. So it's almost like the antithesis of what we've been talking about. So where shall we really design to? That's the first part question. The second part is that if we are designing specifically for CO2 emission, what materials can even be used to help mitigate or stop CO2 emission if we look solely at concrete?
As I said earlier, the real sustainable structure should be the one never built, but I'll let the panel address this. Kochi, do you want to take this? Or
I would like to.
Pass the mic. Michael?
Well, it's an interesting question because you're looking at climate change, but again, part of the question is about emissions, and then the second part is how do you adapt for more resilience. And If I understood, and maybe I misunderstood the question, so we can reduce design for wind speed? Is that what the example was?
He was just saying that we presently design right now at a certain level for winds. But with the change in climate change, if we design to a maximum level and all of a sudden the climate changes again, should we be designing for really a mid-level, knowing that it could change again?
I think the thinking is that this is a very nonlinear process, right? It's a changing process.
You can no longer use historical data.
Right.
That's really what the
historical data can be both good and have maximums and minimums that we're currently not looking at and don't have an answer.
Yeah, I mean, it underscores the importance that, yeah, I mean, historical data definitely has limitations. If that's if that's the downside, the upside is that certainly, certainly in Canada, and I know Canada is not alone, that there are initiatives underway to look at the future-looking climate scenarios, even though yes, there's inaccuracies and whatnot. And trying to zero in and get some of this data to the point where it's specific enough that you can actually use it in local design. So to the point, in one instance you're not over designing or under designing in another. In the case of northern infrastructure, again, because they're the canary in the gold mine. I mean, they're living this right now. O&M, like operations and maintenance protocols and whatnot, are some of the ways that they're addressing load factors right now. You can't retrofit when you've got higher snow loads or wetter snow. You can't retrofit every structure that's up there. But what you can do is bulletproof and revise some of your operations and maintenance regimes, taking snow off of low-rise roofs and whatnot, and putting in better monitoring. When snow reaches a certain threshold, to make sure that you are kicking in with those maintenance techniques. That's the short answer, I guess.
I would like to take that as our last question and take this as I want to thank certainly the attendees here for their participation and question. And of course, everyone which was an online participant, webinar participant, and brought questions in. Some of these will still be answered. We will continue on. I assume truly that will be taken care of, but we will have to conclude the open panel discussion. In concluding, I would like to give a round of applause to our panelists one more time for their help. Thank you.